I'm going to be just briefly sharing the agenda of today meeting. Yes. You can see it now. We have divided actually this the full day. Basically, we have different presentation and also activities. We will start with an introduction where we're going to be having a presentation regarding the IA TAS 73 and some other topics regarding projects that are happening related with PVT development and also deployment. Then in the second section, we will be having more system integration and applications presentations where we will have different researchers and also industry leaders that are going to be sharing our experience with us. And after that, we'll have a coffee break, and then we will jump into modeling techniques for PVT systems, where we will also have really nice researchers that will be sharing with us their approach and how they've been and their experience in doing collector level modeling and system level modeling as well. After that, we'll have a lunch break, and then we will jump into the experimental testing, where we will have different also people and researchers sharing with us the different methodologies and approaches that they have in order to test PVT technologies and systems, which is also one of the course of TAS 73. And then we will have a visit to the Energy Technology Lab here, hosted by Nilsson and Francisco as well. And then I will have a presentation regarding future trends and challenges, and that is going to be about roughly 15 minutes. And then we will close this event today with a very exciting initiative that the PVT4U project has had, that is development of a research network on photovoltaic and thermal technologies and systems that is aiming to connect people. I'm just going to be leaving like that because my team has prepared a full presentation on that. And hopefully this is going to be also a game changer and also a driver for deployment the technology and also increasing the pace of development, which at the moment I think is already quite good. So I think that's we can start actually with the first presentation, but I'm not sure if actually Maria Rando is here, which she's gonna be representing Corvinian for his presentation. So I think Maria is here. I can see you in the screen, Maria. So thank you very much for accepting to present today and to cover Corvinian. So you will have basically the two first presentations of the day. So the floor is yours, Maria. Thank you again.
Okay, thank you everyone for having me here. I think, can I share the screen?
Yes, you can share the screen.
Okay, let me set this straight. I have two screens, so.
Something important to mention before Maria starts, actually Maria is the one that has more time for the presentations, but after that, the speakers, we have basically 5 minutes, especially in this first section of the event. So just for us to have a good timekeeping of the different presentations. So yes, Maria, we can see your presentation now.
Okay, okay, thank you. So yeah, as Ivan was mentioning, I will present for Corvinian and Kramer the overall of the overview of the task 73 of PVT heating systems, and then also subtask D. This is the one that I'm co-leading. So first of all, just as Corvinian wants to start, usually this task presentation is that what to expect in this task. We as hostings or leaders of different subtasks and key as task manager set, let's say, the framework, like when you go to this lunch that you said that you have the table set with the chairs and everything, but all the task participants have to bring their own food, as in they have to bring their own contributions, their knowledge, and add to the task, because everyone is doing this here on top of our work. We are not, let's say, getting anything else than anyone else. So yeah, so this is a bit the start. So who are these hosts? Who are we as task leaders and task managers? So as you can see here, we have people from all over the world. We have Isabel Kosteniuk from Canada. We have Valerie Sejourn from Brussels, from SolarHeat Europe, Frank Bruce from the UK, from Naked Energy, Yang Wang, that I believe he should be around there, from KTH, from Sweden, Corrie de Keyser from TNO from the Netherlands, Corvinian Kramer, that is our coordinator of the PVT task, and from Fraunhofer from Germany, Doug Smith from Coolsheet from Australia, then Raquel and Isabel from both from DEF from Spain, Leticia Brotier from Dual Sun from France, and myself from Italy, also from Spain. I'll present myself later when I do my presentation. So why this task now? The key objectives are to create a factful awareness about PVT heating systems, but we focus here on air and liquid-based systems, to identify and tackle hurdles in innovation systems around the PVT heating systems, to foster and activate the industry and research community on PVT heating systems, and to initiate and multiply PVT heating system installations. So as you may know, there was a previous task, task 60, from 2018 to 2020, that was focused on PVT collectors, and now we come back most focusing on the at the system level for PVT heating systems. So the structure of the task, so as you can see here, we divided it in 4 subtasks. The first 2, let's say, are symmetric. One is focused on liquid heating and the other one on air heating PVT systems. They will tackle with the concepts from product level to system level, as well as different market applications. The liquid-based, more focused on the integration with the heat pumps and on the air heating systems for the fastest integrated HVAC systems. Then we have the other 2 that are, let's say, transversal, that gather also and are very interrelated with the previous 2. Is the awareness and policy. The idea here is to how to talk about it, so also provide facts, explain complex systems with simplicity. It also focuses on publication, the marketing level and scientific level, and on proposal writing. And then modeling and monitoring, there was the one that I'm co-leading, that will address how to simulate the PVT systems, more importantly, filling methodology gaps, how to also provide field installation and monitoring, and transfer them to market through KPIs, and this both for air and liquid systems. So now we'll go more into detail of the 4 subtasks. So subtask A is the PVT liquid heating systems. The leaders are Corrie de Keyser and Leticia Brotier. The main objectives and actions here is to share information on PVT application, collector types, and system configurations, to analyze and document installation and derive the competitive advantage of those, gather a catalog of questions and answers from market experienced participants, and also share methods on how to provide buying decision relevant information. Subtask B is for PVT air heating systems, is led by Isabel Kosteniuk and Qian Wang. The objectives are, let's say, symmetric to the other ones, equivalent, but focus on PVT air systems. Subtask C, PVT awareness and policy, has 3 leaders, is Valerie Sejourne, Frank Bruce, and Doug Smith. The idea here is to provide KPIs for different categories PVT, such as the levelized cost of heat, the levelized cost of energy, the seasonal performance factor, coefficient performance, etc. Also to summarize and present competitive advantages of PVT categories for the end consumers. Provide easy calculations for policymakers on CO2 savings, renewable energy costs, etc. And monitor the market development to provide results, including also the startup scouting. Finally, subtask D, that is the PVT modeling and monitoring, that I'm co-leading together with Raquel Simon, that I believe she's also here and will be presenting later today. The main actions are to apply planning tools on standard cases of A and B, to provide field measurement data in the form of KPIs of subtask C, provide methods for CO2 savings, and also to map and guide through the models in use. So what is the outcome of this task? as you can see here, the idea that Corvina had for this task is that even though we have subtasks, they are all, as you saw, interrelated, and the outcomes, most of them are apart from the different subtasks. So we will have to be very collaborative on during these years and in continuous communication. Some of these outcomes are matchmaking events, also chatbot for answering facts on PVT, an explanation of the KPIs on the Wikipedia PVT page, infographics on PVT heating systems. Also, we want to provide non-technical information on the impact and strategic impact. An online map of the PVT installation, also listing the main KPIs that we'll be selecting during the task. Provide market data for market statistics publications. Monitor the market development and provide results, including the startup scouting and also research radar. So who's working on that? I think for this, probably this project is also helping right now. And here you can see the work plan schedule. As you see, each of the subtasks is divided in different actions. Afterwards, I will explain a bit further subtask D. We started the task the kickoff was in February, this February in Berlin, in Van Fraunhofer headquarters. And as you have seen, you can see here, there are different actions that already started. We are now where the blue line is, and we have the next meeting is in October, so in a couple of months in Zaragoza, in Spain, in ITES headquarters where I work, and I'm co-organizing this meeting together with NDEF. And then, as you see, every around 6 months, we will have a presential meeting at the different participant installations facilities. In each of the meetings, we also usually see some PVT installation, some lab, or so we try to find a spot in which we can see all of that. So who is participating here? So everyone is invited. So if you would like to join, just let us know. As you see right now, we have interested parties from all over the world, from Canada all the way to Australia. The main workforce, let's say, it's in Europe, as expected. With Germany leading the amount of interested parties. Probably there are a lot of people from Fraunhofer here. And then, as you see here, there are a lot of ongoing PVT projects with funded that have been funded. So especially in Spain and also in Sweden. And that's all from my side. So yeah, this is not me. This is Corvinian Kramer. But yeah, I guess he apologized because he couldn't make it. I hope I managed to present the overview properly. And now I will go to the next presentation, which is subtask D. I think I do all in a row, right?
Yes, yes, you can.
Okay, thank you, Ivan. So, yeah, so first now, yes, so who we are, the subtask leader. So me, I'm Maria Rando. I have a PhD in industrial engineering, and I have been working on PVT since 2011, since I started working at Imperial College, and then I continue with PVT all over where I've been moving around. Now I work in ITA, in the Aragon Institute of Technology. There is a public center linked to the regional government of Aragon. We have an extensive expertise on modeling simulation of a wide range of materials processes, multiphysics and multiscale, and I'm co-leading this task with Raquel Simon. I think she will present probably herself afterwards. So yeah, she works in NDEF, and she also has a PhD in mechanical engineering. So as I was mentioning before, subtask D has different main actions. So now we are working on these three that are highlighted here, that I will go a bit more into detail in the next slides. So the first one is to map and guide through the models in use. So here we started with what has been done in the previous task that I mentioned that ran a few years ago, to not reinvent the word, let's say. We did a huge work in report C1, gathering numerical simulation tools for PVT collectors and systems, both the tools and also some examples of each of the different tools. So what we want to do here is to gather this information together with new one that might have come and provide guidelines about which type of models to use depending on specific needs. So it will depend whether you want the model to design a PVT collector or to design a system or size the system or even run some annual performance optimization. All of those need different software. The second action is to to provide monitoring guidelines and KPIs associated. So in this one, we want to provide field measurement data in the form of KPIs that will be decided in subtask C. So when we start of what was done in previous task 60, as you see here that we did, again, a big effort in report D1 that is published, you can find it in the webpage, with a lot of different KPIs for the PVT collector field, for the solar fraction, as well as for the rest of the components or more transversal, such as for final energy savings or environmental KPIs. The proposal for this task is to focus on field monitoring data from real installations. So what we divided here is KPIs for market level and for research level. So started at the market level. So first is which are the desired KPIs. Then we will decide which are the magnitudes that needs to be measured to provide to calculate these KPIs, and which are the commercial sensors that are needed to measure these parameters. And here we want to provide useful information for the customer that wants to buy the PVT. Also, KPIs on the energy performance that are interesting for a customer, and ask what has a real impact on economics. Then at the research level, we will investigate more other interesting KPIs, then which systems have been used in literature and which extended sensors are needed for that. For the third action, basic calculation methods for CO2 savings, again, we start from what has been done. There were several KPIs that were defined during the previous task about, say, fuel cost, avoid global warming potential, and primary energy consumption. And what we want to do here is to provide a calculation method for CO2 savings based on the energy generated, both electrical and thermal. For this, as you know, we need to apply conversion factors from energy to CO2. They vary from country to country, and there might be also some international factors. So we want to develop a reference list of reliable sources. Finally, for the guideline for planners, design and standardization, here the idea is to apply planning tool on a standard cases of both air and water and liquid PVT systems. We divided it in 3 phases. The first one of the definition. The idea here is to provide guidelines on which solar panel is more suitable. It depends, as you know, on a lot of different factors, such as the thermal loads, the electrical loads, the roof on space requirements, the temporal consumption profile, or other interaction that might need with another equipment. So we also want to answer the question of when it is interesting to install a PVT system versus a solar thermal PV. It might be the case that it's not worthy, depending on all of these factors. Next stage, it will be the design. So the idea is to provide guidelines for professional markets of which steps they have to follow to design and size a PVT plan of both air-based and liquid-based PVT. Here are the standard factors that we will say was analyze the energy consumption, the solar potential, and also do the matching of generation. And again, gathering all this information from subtask A and B. And finally, for the standardization, we have standard cases A and B. We have a big starting point, which is the task 60 again. So the idea is to provide these standard cases based on the environmental condition, applications, location, or legal restrictions. So what is next? Right now, for the first action, we would like to collect experiences from collaborators. Then we'll be listing the tools and sorting them according to complexity and easy to use. Our idea is in the next month to prepare a gaps in modeling report and how to solve these gaps, and also suggestions how to reduce complexity. So from experiences to decide which effects should be modeled and which ones don't need to be modeled, depending on the use that you want to do to that model. And for the other ones, we would like now to define and select integration schemes based on 3 locations. We started with these 3: Mediterranean, Nordic, and Central Europe, but we might extend it if we see it is necessary. And then we would like to provide examples of PVT integration schemes at market and research level. So I think that was all from my side. So if you have any ongoing projects, I see today there will be several projects being presented here that probably have and could contribute to the report. So please let us know. Here, this is the main contact for the PVT task. You can also contact me. And yeah, that's all from my side. Thank you.
Thank you very much, Maria, for the very nice presentation and to update us regarding the task and the subtask that you're leading as well. Now we will proceed with the next presentation, which is actually me. So I'm gonna be sharing my screen quite soon. And we will start with the presentation of the first project on PVTs, which is PVT for you. And wait. Here. Yes, you should be able to see it now, right? Great. So, but it's not, it is a bit, yeah. So yeah, we'll have 5 minutes to present that, as well as the other presenters of the project. So as I mentioned, I had the opportunity to present PVT for you, which is a research project that was funded for the very first call, joint call of the Clean Energy Transition Partnership program that was in 2022. It is a 1.1 million euros project where we have 6 institutions working together from industry, research, and academia. We started in September 2023, and the end date is going to be on August 2026, so it's basically in 1 year. The main idea of the the consortium distribution is the one that you can see here. We have institutions from Sweden, especially three startups, including us, Solar Peak Solaris, Renewables, and MG Sustainable Engineering. And we are also collaborating with the University of Gävle. We have also the Technical University of Denmark and the Laboratory of Renewable Energy and Geology in Portugal. And all of them are basically trying to work towards the deployment of PVT technology. The motivation behind it, I think that many of you are quite aware about this graph. I think that nobody that is in PVT or solar thermal and don't know about the Solar Heat Worldwide report. And this is, I think, that the latest figures that we have from the report. So far, we have 1.67 million square meters installed of PVTs, and those numbers have been increasing in the last years. Nevertheless, PVT technologies still need to enhance their competitiveness and also expand their applications to other sectors. And another thing also to increase awareness, which is the main motivation of PVT for EU. The main objective of the project is to develop 2 PVT technologies, one that we call a PVT-SP or Solar Peak for the company that is developing. And this is basically a PV panels retrofit that is aimed to be attached in the backside of current infrastructure of PV panels in order to transform them into PVT collectors and collect that heat that otherwise is wasted. And we have the second one, which is PVT-MG, which is more for industrial applications up to 140 degrees. And in this one, we're trying to upgrade a previous version of the Solaris collector that has been in the market or was in the market in the last decade. And we're trying to find a much better and most cost-effective also solution for this collector, targeting high performance, cost effectiveness, and low environmental impact as well. The progress that we have so far in like after 2 years of the project, we have already like the 2 first versions of the collectors tested at the Technical University of Denmark. These are graphs and photographies shared by them, and also the experimental characterization of the efficiency for both collectors. We have been working also on how to improve the electrical design, the thermal management as well of both technologies, and also to include within the design and redesign of these collectors the environmental part and the life cycle assessment approach during the design, because the idea is that we reach a version 2 by the end of the project. For the prototyping, we have been also looking into the PV cells configuration, trying to find out which is the most, not only the most efficient, but also the most cost-effective solution that can also be reliable and can withstand the operational characteristic that a PVT collector of this characteristic should have, and aiming not to have a solidly solar thermal collector after 5 years. because the PV part will not work. And another thing that we are also working a lot is to increase awareness and connections about PVT. You know that PVT, I think that has been growing a lot since I started also doing my first research on PVTs. That was like in 2012, no, 2013 actually, a bit later than Maria, I would say. But right now and today, actually, we're going to be launching a research network that is trying to make these connections more straightforward, so we can know and we can identify which is the research and which is the strategies that some other researchers or institutions are doing around the world, so we can connect each other and learn from each other, so we can also increase the pace of innovation and deployment of the technology, which is also one of the main objectives of these projects. So I think that is it from my side. I think that I kept it in 5 minutes. And if you want to follow us in LinkedIn or in the website, you can do it. We are quite active, and we are always trying our best to keep both the website and our LinkedIn pages up to date. So that's gonna be all from my side. And now I'm gonna be giving the floor to the next speaker, which is actually Georgios Aspetakis, right, from KTH.
Yes, I will step in for Chen. He couldn't make it.
Yes, and so then I will give the floor to you, and you can share your screen and limit your presentation to 5 minutes, George, please. Thanks.
Okay, cool. So first of all, I would like to thank Ivan and the team for the opportunity to present our project. Okay, what's this? And I would like to introduce then Double Up, our new project with project owner Einar Mattsson and project manager KDH Byggvetenskap, where we will focus on the integration and the control of PVT customized to the Swedish housing market and the Swedish climate conditions. First of all, let's begin with the financing. So Double Up is co-financed by Einar Mattsson, KDH Byggvetenskap, SBUF, Bravida, and Uponor. And you can see here our group working on this, ranging from different fields. Here in the audience is also our newest addition, which is Larussi. He's a new PhD student here in KTH, which will be working on this project as well. And the research question of Double Up is whether we can find out the double benefits which we can get by combining PVT with the HVAC system in buildings, and what can the surplus values be for the property owners and the installation industries as well. So what else can they get from this, and why we should push for it? So Double Up is a high TLR project, and it's close to the market. So we are targeting mostly construction industries, property owners and operators, VVS and other installation providers, of course, PVT manufacturers, and then even architectural designers. And then we have these partners which have stepped up to the challenge, and they have joined the project, and they provide feedback to what we present to them. So the vision of Double Up is to help construction industry and the VVS industry with correct decision making on how PVT systems should be integrated into the buildings here in Sweden, as well as the control, which can be even more complicated. So just a short reference to the timeline. So what we have done so far this year in 2025, we collected data from an existing facility of Einar Mattsson. And we are right now doing some preliminary simulations and testing, where we will assess some integration scenarios. And that will lead to next year, after having successful simulations, to test in the selected facility of Einar Mattsson, where we'll further develop the models and validate them, validate the simulation models, and in continuance also develop the control strategies, and then start looking into the scalability of these during 2027, where we'll look into that And then after discussions with different stakeholders, we will finalize our business cases for the Einar Mattsson building case. And yeah, here you can see some pictures of the facility and what we are aiming to do, and also a silly picture of me testing some PVT, but that was some years ago. This will be taken on by our new PhD student soon enough. The project has already kicked off in winter, and we welcome new partners to join if they wish so. And with that, with that opportunity, I would like to invite you to follow the progress of Double Up. And we are going to include some of the results in the task 73, which was presented earlier. And hopefully this will go all very well. And it's all very good to see you, see some very familiar faces in the audience. Thank you from my side.
Thank you very much, George, for the nice presentation regarding Double Up, which in particular for me is quite interesting how you're going to be integrating also the construction sector into and working together to understand how PVTs can be integrated and can create value to property owners as well. So thank you for that. And now I will give the floor actually to Francisco and Nilsson, actually, sorry, regarding the project that is called Smart Reno. So Nilsson, the floor is yours.
Hopefully this is loud enough for the mic to pick us up. Good morning, everyone. And this is another KTH project, different department. This is in the Energy Technology Department. This is now our 5th project on PVT, about 10 years of work going back and forth between collectors and systems. And this is now our most, I'd say, market close systems project so far, called Smart Renovation Strategies for Sustainable Electrification. It's funded by the Swedish Energy Agency in partnership with Bengt & Gren engineering firm, 2 PVT companies, Samster and Dualsun, as well as a behavioral design firm, which will be a bit of an oddball there, but you'll see in a second why that is. So the problem that we're targeting is that Sweden was a very early adopter of ground source heat pumps. So there was a large wave about 20 years ago, and with the shock in the electricity prices and the age of these systems, a lot of people were looking to upgrade. But these boreholes are now too short to support a new ground source heat pump, and you end up with a lot of backup heating and high power peaks due to that. And so to help solve that problem, we're looking through all the different renovation options to then get the most out of modern ground source heat pumps. A long list of options here. Of course, PVT, borehole regeneration with PVT is a key part of that, but also specifically when it comes to the peak power problem, there's a demand response, storage, that sort of thing. So we're not necessarily exclusively looking at energy efficiency like we have in the past. We're also interested in peak power demand as well. There's 3 main work packages that we've got. So one is using a really interesting borehole model that was developed by a former colleague of ours at KTH, where instead of the traditional borehole models that many people have used, where all of the boreholes are installed at one time, here we can add them at different times and have different properties. It was originally developed for doing neighborhood interactions, but here we're using it for a single system. And so that's being adopted to be worked with our systems models in Transys. We're also looking at underground phase change, so it's ice storage. So we're looking at a PVT heat pump system that's not connected to boreholes, but also exclusively connected to a underground store. So that was constructed this year, and we'll be simulating that. We're in the process of simulating that as well. And then we have a lot of empirical data, not only the thermal store, but also many years of existing systems to then do empirical validation of our systems models. We're using Transys like many folks. So we've got type 203 as our PVT model, populated with characteristics from our lab. This was a model I made for multifamily houses that's now been adopted for single family houses. And we're moving forward with that. And like I said, we're not just interested in efficiency, but peak power and power management, as well as price, managing the system for volatile pricing and that sort of thing is of keen interest to us. And then the last phase is getting feedback from the actual people who would be buying these systems. So this is where Bitinda Labit is our sort of behavioral partner in this. We've worked with them in the past to great success. And so all these system simulations will be presented to actual homeowners as alternatives, get their feedback on sort of, not just the technical KPIs or the economic KPIs, but also, do you mind having your entire garden dug up to stick a giant tub of ice underneath the ground? Things like that. Do you think solar cells or PVT look bad? These types of things to get a realistic trade-off of their biases, not just about, solar fractions or payback times. There's this social component as well. Kicked off the project last year, so the geoenergy model and the thermal stores have been installed. We're moving very quickly now. Those are being integrated to our Transys model. System simulations are very heavy this year and into next year, and then we'll be doing the interviews mostly in 2026. I think a lot of these results will also be in task 73, and yeah, tried to keep her prompt. So that's it. Thank you.
Thank you very much, Nilsson, for the nice presentation regarding the project. It's very nice. Every time that I see a presentation, I get excited about it, but it's very nice. And I think that with that, we conclude the project's presentation regarding PVT. Sorry, we have like so short time on that because we wanted to accommodate time for other topics as well. Nevertheless, I feel really, it feels really nice that how PVT is developing not only at the collector and system level development, but also the social acceptance where we are going to be assessing other things that usually research are not looking into it, especially the ones that are looking to increase the efficiency of a certain technology. So with that, we can jump into the second section of the event, which is basically integration and system integration. And I will give the floor now to Francisco Beltran, and he will be talking us regarding the integration of PVT systems with heat pumps. So Francisco, the floor is yours.
Thank you, Ivan, for the introduction. So my name is Francisco Beltran. I'm a PhD student working with Nelson, also at the Department of Energy Technology.
And it's over. Thank you very much.
That's all I have to do. Yeah, so this is us. So just to give a picture of where we are working at. So KDH, Industrial Engineering and Management, is the school we belong to in the Department of Energy Technology. And within the Department of Energy Technology, we belong to the Division of Applied Thermodynamics and Refrigeration. The division is led by Associate Professor Hatzet Madani, who is also my main supervisor. Then we work in a team with Nelson as well, who started working with PVT several years ago. And then I'm building on Nelson's work with my PhD, which I hope to wrap up soon. So why PVT and heat pumps? So we all know that we need to decarbonize the heating sector, and 80% of the building energy demand in Europe is due to space heating and domestic hot water. And I think we can all agree as well that for space heating and domestic hot water, for space heating, at least heat pumps are one of the most efficient technology, especially in a fully electrified scenario. And there are 190 million heat pumps. This is data from 2021 installed worldwide. Then, according to one of the IEA's net zero by 2050 scenario, this number is going to increase to 600 million. So this presents an opportunity for PVT to be integrated with this technology that is going to be continuing to scale up fast. And then also the cost of PV is declining. So there's an opportunity for the solar thermal industry to take advantage of that declining cost of PV as well. So also there's some barriers to heat pump adoption. For example, in browser heat pumps, we are thinking of a city. There might be a lack of land available for drilling holes. And then also we know that digging the holes for the ground source heat pump ends up increasing the investment for these systems. Then for air source heat pumps, there are complaints about the noisy heat exchanger, although they have been getting better. They're still producing noise, and especially if there are several of them together in for example. And then during cold days, the efficiency of air source heat pump can drop considerably. And then we have exhaust air heat pumps as well, but not all buildings, very like few buildings have ventilation. So then there are a few ways in which we can integrate a PVT plus heat pump systems. Here I'm trying to keep it simple. One of them is having them in parallel. For example, having the main source, which could be the boreholes, for example, in a ground source heat pump, and then having the PVT working in parallel connected. Then you have the series integration of a PVT, and here you can see the diagram, the PVT acting as the sole source of the heat pump, so they're connected in series. And then we have like a subgroup within the series connection, which can be the series regenerative. And it's you can see there that the PVT can act both like as a source for the heat pump, but also any excess heat that is being generated by the PVT can be stored in the ground, or that can be used to heat up the temperature in the borehole, regenerating the ground. So then one of the things I've been looking at the most during my PhD is which PVT should we use for when we are integrating it with heat pump systems. So for that, we had used thermal performance coefficients. There's like probably you're all familiar with the ISO standard equations on how to derive the empirical coefficients of the sort of the performance curve of the different PVTs. So here we're using a simplified version because we have a testing facility here at the department. And we have, if we look at this equation, we have this term here, which is the zero loss efficiency. And then we have the wind dependence of the zero loss efficiency. And this sort of represents how well the PVT is changing, capturing heat from the sun, solar radiation. Then we have the first order heat loss coefficient and the wind dependence of the heat loss coefficient, which are multiplied by the temperature difference between the mean fluid temperature and the ambient. So this shows sort of how well the PVT is at exchanging heat with ambient air. And then we have the effective thermal capacity, which of course is related to how the PVT is manufactured, what material we are using. And then the preferred, this is very important, you probably all know, but the preferred coefficients depend on the application. So there's no like best PVT, it depends on what application you're thinking of, which PVT you should use. And then this is just a verification that usually the C1 plus C3 times the wind velocity is referred to as the U value of the PVT in the. So this is what we have found from simulations and also from other research. So for parallel systems, usually glazed and insulated perform better because you have lower losses to ambient, and then you can get higher outlet temperatures when you can use to heat up the tank to higher temperatures, or even supply domestic water directly. And then in these cases, you want a high zero loss efficiency and a low U value because you want to minimize heat losses to ambient. Then for series and series regenerative configurations, would be better off with an unglazed and uninsulated, also known as WISP collector, because since the temperatures in the PVT circuit are quite low, for most of the hours of the year, you can capture heat from ambient air. So it's not a liability, it's more an advantage that you have this high U value. So for PVT source, we want, of course, a high zero loss efficiency, but it's super important to have a very high U value because we want the system to be able to perform and supply the heat to the heat pump even at low ambient temperatures. And then for serious regenerative, there's sort of a trade-off. So you want high serial loss efficiency, but also you want a high value. And then this is how you should design, based also on our research, how you should design a PVT when you're integrating it with a heat pump system. So for ground source heat pumps, we have found that one of the best things you can do is keep the collector cheap, since it is supporting the borehole. So the borehole is the main source, and here the PVT is regenerating. The electricity savings are small. So then if you use an expensive PVT collector for this purpose, it's not going to. Material choice is secondary. So here we have found that the plastic can perform well compared to metallic counterparts. But then what's most important is the heat exchanger area. How much heat you can capture from, how much area you can have in contact with the ambient air, but also in contact of the fluid with the back of the PV panel. And then this is something important as well, the total heat yield outweighs the timing. So how much heat is generated over the year for these systems is more important and more critical than when the heat is generated. It doesn't matter if you are generating heat when the heat pump is not working, because we have the borehole acting as some sort of a thermal storage, non-thermal storage. And also something we found is that modest-sized PVT arrays usually suffice for this purpose, and then the rest of the roof could be used, could be covered with PV only, for example, systems. And then for the PVT source heat pumps, since it's the only source, the PVT, then higher cost designs are acceptable. So there's a higher chance that you will get your money back if you invest in this. Then thermal conductivity and thin design become vital. So for these ones, material is more important, because you want a higher conductivity, because it's going to be your only source of heat. Then here the heat production timing is critical, because of the thing we mentioned, that the PVT is the only source of the heat pump. So the heat must be available when the heat pump runs. And as I was mentioning before, unlike a borehole, there's no long-term storage here in the borehole here. And then larger collector arrays are needed, especially to be able to supply heat with these peak power periods. And the biggest potential for PVT heat pump systems in Scandinavia, for example, rescuing cold boreholes. So borehole systems have been operating for several years, use PVT to temperature and extend the lifetime of the borehole. Then supporting undersized boreholes in land-constrained buildings. For example, if you have a building in the middle of the city that doesn't have enough space to drill like a fully sized borehole field, maybe you can drill this number of boreholes, but support it with PVT. And then also keeping an eye on PVT sourced heat pumps. We saw it at the workshop last year when at DTU, when we visited Metrotherm. There are several companies that are designing PVT sourced heat pumps with a lower temperature. So then in that case, PVT would be a competitive alternative for like ground source heat pumps or air source heat pumps. And then in Central Europe, PVT source heat pumps are a big thing. And then also you could rescue cold boreholes there as well. And then in Southern Europe, the parallel connection is predominant, I would say. You have more sunshine hours and higher temperatures. So then you can use the PVTs directly to supply domestic water, for example. And they're quite popular, for example, in hotels or sports facilities. And I think since it's 10:45 and I will have another presentation later,
Yeah.
I think I can go through these afterwards, so we catch up with it. Yeah,
Great.
so just this slide, I think it's important. So why series regenerative PVT plus ground source heat pumps? So there are several benefits, but something that's important to understand is that around 600,000 ground source heat pump systems in Sweden we have right now. And then there are 20,000 new installed systems per year. So in these applications, coupling PVT with regards to heat pump systems, it presents like a huge opportunity, and there's a huge market potential for PVT integrated ground source heat pumps. Yeah, so that was it.
Thank you very much, Francisco, with a very nice presentation and interesting as well. I really like what you mentioned regarding there is no best PVT, right? And it depends directly on the application. And I think that we inherit also that statement from solar thermal collectors. But I think in this case with PVT, it's a bit more complex because we have an additional, well, for the inherent dual production with PV as well, right? So I think that is something that we need to keep in mind, and that we will still elaborate more on that in the next presentations. So with that, we can jump to the next presentation, which is gonna be presented by Raquel Simon from ENDEF, and it's regarding PVT system for domestic hot water and space heating in buildings. So Raquel, you can share your screen and start with your presentation.
Okay, thank you to everyone. One moment. I think you should be.
Yes, we can see it now.
Great. So, hi everyone, my name is Raquel Simon. I come from ENDEF Engineering with ENDEF Solar Solutions, which is a solar energy company located in Spain. We are PVT manufacturers, and I'm here today co-leading the subtacti as Maria presented in the task 73. And I'm here to present today the PVT systems for domestic hot water and space heating in buildings. So, previous to everyone, previously I want to share with you some data presented in the last Solar Heat Worldwide of presenting of this year, with the data coming from last year. In this report, as we can see, almost 70% of the newly collector areas installed regarding PVT are oriented or focused to buildings in the form of domestic hot water, space heating, or combined to other devices. From this data, from these collectors installed, we can see that most of them in the last year was water-based, with a small section of air PVT collectors, which were quite important installations some years ago. But after the close of one company in France, the last years there was almost no air PVT collectors installed. It's true that in this data that I'm sharing, this a little bit suspicious that there is no data for concentrated PVT collectors or evacuated PVT collectors, which we know from the last Eurosun that there are some installations regarding that, but I guess that this data was not able for this report. Another conclusion of this report was that after 2 years of market drop in 2022 and 2023, it seems that there is a slight recovery in the last year. So it seems that the PVT market is currently in a phase of consolidation and strategic realignment. However, if we go to the reality on the PVT field, which installations of PVTs are installed in the real market, far away from researching projects and approximations, we can see here the amount of articles in the last years, at least coming from the Science Direct, and also the new installations that we have from the last years. What we see is that it's been a lot of research regarding PVT field, regarding collectors, systems, different integrations, and modeling, but there is not so much installation in reality. The ratio that we have is that there is almost one article published per 6 square meters of PVT installs, which is quite disappointment, I guess. So why this happens? This happens because it seems to be a bottleneck between the lots of research that is performing, but it seems to be some problems for the real installation of all these models that are being analyzed. The barriers for adoption have been pointed out in different studies and also by different manufacturers. We can talk about what's needed further research on integration, on real integration. There is a lack of studies regarding long-term installations, since there is kind of a novel technology that it's been applied for the last 10 years or so, but we don't have results for a long-term studies. There is also a lack of awareness by not only by general public, but also by installers. It's not so easy to find installers able to cover both sides of the installation, both electrical, both thermal, and it's difficult to find installers that are willing to address both sides, or at least one side, without knowing how to address the other side. There is also a lack of standards and policies regarding PVT, which provokes that some subsidies are not able for the PVT market because they cover only PV or only thermal, and PVT can't not compete with these individual solar technologies in terms of subsidies. And finally, it's always the economic viability. We all know that PVT collectors can be a great solution for many systems, but sometimes the economic viability and profitability is a problem. Regarding this, we have to take into account that that in most cases, PVT modules, are less than the 50%. It's the half of the cost of the full installation. There are other components such as the thermal storage tank, the electrical inverters, the other hydraulic systems, or mainly the labor that cover complete this cost, and we all have to take into account all these costs that usually are not taken into account. With all of this, I don't want to discourage you to install PVT panels, but I just want to emphasize on the importance of make feasible studies. It means that all the models and the systems that are studied need to be feasible and transferred to reality. Because of this, I'm presenting here some. Well, I'm going to cover the main PVT systems that based on application on buildings, and also some learning tips or learning field for PVT operation and installation. Some questions that we have to take into account when address an installation, and also should be taken into account during the modeling phase. Regarding the applications that we have in this presentation, we have the domestic hot water and also the space heating. If we talk about domestic hot water application, we are only talking, or mainly talking about water-based PVT collectors, since the air PVT collectors don't cover these dwellings. In the domestic hot water, what we have is that a desired temperature between 45 and 15, but because of safety, sometimes in some countries, some cities, there are some regulation that states that the desired temperature has to be higher, around 60 or even 70 in some cases, for safety of Legionella and this stuff. So in this case, the PVT collectors can work as a preheating mode of the domestic hot water, since the inlet source for the PVT collector is coming from the mains water. I've included here two main schemes that are possible: the open loop, when the water in the solar circuit is the same one that's in the demand circuit, and the most useful, which is the closed loop, when the solar circuit works in a closed loop, which is usually more recommended because of the safety issues of the installation and also the consumption of the people. If we talk about the space heating, we can talk about water-based PVT collectors and also air-based. In this application, what we have is that the desired temperature depends on the heating mode that we have on the building. If we talk about traditional heat emitters, the desired temperature was too high. But if with the novel technologies such as radiant floor or novel heat emitters, the desired temperature in the output in the demand is lower and can be reached by the PVT panels. However, the bad news about the space heating is that they usually work in a closed circuit, which means that we are not possible to preheat the water, because the inlet temperature that we are coming, or the return temperature that we are coming from the demand, it's around 30 or 35 degrees. I've included here two main systems: the one combined with the hot water when the solar heating can go for both applications, so domestic hot water and space heating. It can be with one storage tank or two. I mean, this is a simplified model. And also the combination with heat pump. I'm not going into detail on this because we had this interesting presentation from Francisco, so I'm not going into more detail. If we are talking about the air PVT collectors, what we have is that there are different operation modes if we are talking about heated or already heated or not heated spaces. If the hot coming from the air PVT collector can be driven directly into the house, or can be in combination of the heat recovery kit as a preheating of the air coming from the building. Also, there is the possibility of combining the air PVTs to a heat pump. This is not so seen in the real market, and it's mostly addressed in researching projects and researching field. Then, regarding the learning pill or the grandma tips that I'm going to offer to you, I propose here you have the main scheme of a water PVT system. When you have the main components such as the PVT collectors, the solar inverter needed for the electrical production, the pump and the storage tank for the water production, and also the auxiliary heat device in order to reach the desired temperature. If we are talking about circuits, what we have always is the primary circuit, which is the solar one, and the secondary circuit, which is the one for the demand. Additionally, it can be a storage circuit, which can no exist, or can be composed by different storage tanks. If we talk about the primary circuits and we address the hydraulic connection, the first thing that we have to say is that it's usually driven by a circulating pump, which is called the forced circulation, but it can be also in some cases that there is no circulating pump, which is the case of the natural circulation. The production is much lower, but it's for cases with no electricity or this kind of special cases. In the solar field, what we have to take into account is that the system has to be balanced. I mean, you can connect the panels from the hydraulic part in parallel or in series. In parallel, you will have higher amount of flow. In series, but lower temperature. In series, you will have higher temperature but lower fluid flow. But the first recommendation is to have the solar field balance, which means that the pressure loss that you have in the different benches are similar in order to have the same amount of flow and your solar field working properly. Another hydraulic components that need to take into account are the high blades to let escape the air bubbles that we have in the installation. Remember to locate them in the higher point of your installation from the physical aspect. The presence of the heat sink, which is a device used to evacuate the excess of heat that we can have on the installation. This is very interesting this is required for those places where it's expected that there is no heat demand for a period of time. Even in the cases that are long duration and that has a daily operation, there is always some places for vacancies, holidays, Christmas, weekends, where there are days with no heat demand. In those cases, there is always very useful to have a device for evacuate this heat in order for the safety of the installation and also for the safety of the collectors. Or something similar happened with the anti-freezing, which is very recommended for the Mediterranean climate and totally required for the north. Okay, the central and north of Europe. There are also other components such as expansion vessels and valves, which please do not underestimate them because they are very important to guarantee the operation and the safety of the installation. Defining the operation controls is going to define not only the safety but also the production of your installation. It can be centralized, a market one, or a customized. The heat exchanger can be installed inside the storage tank or as an individual component. And also remember that from the electrical connection, the right dimension of the strings in order to not to have any production penalized. The solar inverter, which right now we have more modalities. It can be in the micro inverter, and also we can install optimizers to not to lose production in case of different lines, and the connection of the solar inverter, which can be feeding with the electricity is fed into the grid or off grid. If we talk about the storage tank, the importance of this storage tank relies because depending on the sizing of this tank, it's going to condition the temperature, the working temperature of the PVT panels, which in the end refers to the thermal efficiency of these panels. There are a lot of accessories that we can have, like the heat exchanger in the different circuits, or maybe temperature probes, thermal insulation, the stratification of the storage tank, or also the connection of the auxiliary heat device, which can be connected in the upper side of the storage tank, or in line with the storage tank, just before the demand, but after the storage tank. In the case of more complex installation, we can have different storage tanks with regard to the output temperature, like for different applications, domestic hot water, heat pumps, space heating, and so on. And regarding the thermal demand, it's difficult to talk about this because it's strongly dependent on each particular case. So it's going to vary. I mean, this is like the most simplest way that we can have, but it's never going to be like this. The thermal demand from the hydraulic part totally conditions the temperature operation of the collector, and thus it conditions the thermal efficiency and the production. This is a concept that from the people that we are working on solar thermal, we understand that, but for most of the people on the market, customers and even companies, engineers and architects, they don't understand. They ask you to provide how much is going to be the production of your panels, and they don't understand it is going to be conditioned by the thermal demand. Regarding the demands that we have in a building, we have to say some words about that. We have the domestic hot water and the space heating. The pros of the domestic hot water is that allow preheating, but the drawbacks is that there is usually low demand in residentials, only sometimes irregular. And also for the space heating, we have more regular demands, but only during only during winter, because it's a seasonal. So there have to be another application for the heat during the summer. Yes, some desired applications, those that have a high and constant thermal loads, such as hospitals, hotels, sports centers, nursing homes, and all that. Regarding the RPVT systems, it's still is not so standard. Yes, I'm going to
sorry
finish.
to interrupt you. Yes, exactly. Maybe we can finish in one. Yeah, thank you very much. Sorry to interrupt.
1 minute, and me finishing. Okay, I'm sorry. I want to talk about a lot of things. I want to tell a little things. Yeah. So regarding the RPVT systems, it's just as we said before, there are different modes to connect if it's heated or not heated space. And in this case, the main problem is that it's difficult to store the hot heat, the hot air. So the consumption in most of the cases has to be direct. I have here there's some light at the end of the tunnel, so I've shared with you some examples of success installations, two coming from NDEF and the other one from the Olson of Abora, which are 3 companies that right now are installing PVT panels. And that's all from my side. Thank you, Ivan.
Thank you very much, Raquel, and sorry again for interrupting you. It was a very nice presentation. I really like how you put also, and you made the comparison between research production with installation. I think that was quite something that I've never seen before, actually, to be honest. But it was quite nice.
Something new.
It's an important measure. It gives us a dimension of where we are still, of the level where we are and where we need to be in terms of installations.
And the gap between both, actually, right?
It's something that is planned to be not covered, but at least addressed by the task 16.3. So we are in the path. We are on the road.
Great. Thank you very much again, Raquel, for the nice presentation. Then we will move forward with the next presentation, which is going to be given by João Cardoso from LENEC, and it's going to be about shifting a bit more the applications towards industry. So I will give the floor now to João, and yeah, the floor is yours.
Okay, thank you very much, Ivan. So, yeah, my name is João Cardoso. I'm from the Energy Efficiency and Renewable Energy Unit of the Portuguese National Laboratory for Energy and Geology. And with this presentation, I would like to motivate a little bit some developments that we are trying to make in the PVT4EU project, targeting the use of PVT systems for industrial applications. Up to now, what we have been seeing, and I think that what we are going to see afterwards is targeting the residential, or better said, the building sector, which is a natural target for PVT systems given their characteristics. But I'm going to try to motivate a little bit the study of these applications of PVT systems in industries. Okay, so the industrial sector is in worldwide level is the largest sector in terms of final energy consumption. So it represents a little bit more than 1/3 of the total final energy consumption in the world, and only 18% of this energy comes from renewable energy sources. Heat consumption represents the vast majority of the energy that is of the final energy that is consumed in industry. In this case, it's in 2022 it represented up to three quarters of the total final energy consumed in industries. So this is actually a sector where the use of heat and the production of electricity can be very, very interesting. Also because it's a hard to decarbonize sector, particularly for very high temperatures. Solar heat actually represents 1.2% of the heat consumed by the industries. So it still has a lot of potential to grow, including also in PVT systems, as we are going to see afterwards. If we look to the different industrial sectors, we can see that the electrification rate is different amongst the different sectors, of course. But we can also see that the largest energy consumers were the iron and steel sector, the chemical and petrochemical industry, which both of them together represent roughly 1/3 of the industrial energy consumption, followed by the non-metallic minerals industries. This includes, for example, the glass, the ceramic, and the cement industry, with approximately 13% of the energy consumed by all industries. And then with a much lower share of the energy consumed in the industrial sector are sectors like the food and tobacco, which is actually the fourth largest sector at 6.5%, the non-ferrous metal sector with roughly 6%, paper and pulp, and then mining and quarry. These at world level. So if we look to the industrial sector in the European Union, there is a slightly different picture because less energy is consumed in the industrial sector. So in the EU, industry represents 1/4 of the final energy consumption. So, and we can understand these, right? Because most of or a large quantity of the manufacturing and the production, industrial production, is located in countries outside of the European Union. So that's why we have these lower share associated with industry in the EU. And although detailed statistics of heat consumption in the EU industrial sector are unavailable, the estimates that are made based on different methods like surveys or bottom-up models conclude that the share of heat in the EU industry represents somewhere between 60 to 70% of the final energy consumption. So again, a large quantity of the final energy consumption is as heat in the industries. We can also see, and this is what I'm trying to show here. We can also see that although there is in the EU a 26% of renewable energy share in the heating and cooling sector in 2023, which is the last year for which we have data, we can see that direct renewables consumption in industry is lower. So it should be somewhere between 11 and 15%. Of course, that there is the electrification here helps because the EU has a large share of electricity, almost 50% at the moment is within 45%, comes from renewable sources, which so as we are electrifying our industry, we are, let's say, also decarbonizing and introducing more renewable energy through this energy vector. But, what I wanted to show you is actually looking here to the total final energy consumption by industrial sector. And here we see some changes, namely the largest sector worldwide, which is the iron and steel sector, is now on the EU only the 5th sector. So the largest industrial sectors in terms of energy consumption are the chemical and petrochemical industry, with roughly 22% of the total energy consumed. The non-metallic minerals, paper and pulp, so both of them roughly with 14%, and then the food, beverages and tobacco industry with 13%. And as I was saying, the iron and steel, which decreases significantly in terms of its relative position, to representing only 10% of the final energy consumed in all of the industries in the EU. And this is actually something quite interesting because if we look to the heat demand and the temperature level at which this heat demand occurs, what we can see is that we have the largest share of heat demand, so more than half of the heat demand occurs at temperatures exceeding 500 degrees Celsius, which is these ones here represent bars on red for the different sectors. And of course, that this means that these temperatures cannot be addressed by PVT systems. And so we need to focus on different applications. So we can also see that roughly 25% of the heat demand occurs at temperatures between 100 and 200 degrees Celsius. And then the third largest heat demand occurs at temperatures below 100 degrees C. So this is roughly 12.5% of the industrial heat demand here. And this is interesting because this is the very suitable temperature level for PVT systems. And if we look to the distribution of these heat demand and the associated temperature level in the different industrial subsectors, we can see that it is very different. And for example, we have some sectors which have large shares or larger shares comparatively of heat demand at temperatures below 200 degrees C, these ones here on orange, or even below 100 degrees C if we look to these purple columns here. And what we can conclude here is that, for example, one sector is highlighted, is that the food, beverages and tobacco sector, where a high share of heat demand occurs at temperature below 100 degrees C, and also a significant amount of heat occurs between 100 and 200 degrees C, which makes this sector a suitable target sector for the PVT deployment. So here, if we look now in terms of the processes and the temperature level of the industrial processes, we can see again that the food and beverages have several processes occurring at temperatures below 100 degrees. So these are processes like blanching, scalding, pasteurization, cooking, some of the drying, not all, but washing, tempering. So a lot of industrial processes occurring here at temperatures that are interesting for PVTs. Also, the preparation in these is across the different sectors of makeup water, preheating and washing systems are also very interesting processes to be addressed. Also, in the fabricated metal, we can see that a significant amount of processes from pickling, chromating, degreasing, electroplating, and so on occurs at temperatures below 100 degrees C. Also in the textile sector, for example, the bleaching, coloring, and washing are also suitable targets. So when we look at these, we think, well, the industrial sector needs electricity. There is a big drive today to install PV systems in industrial facilities. Industrial facilities have limited area for the deployment of solar technologies. So why shouldn't we also think and consider the development of PVT systems applied to these sectors, having the heat produced in cogeneration with the electricity? And so, as the previous presenter, as Raquel also addressed, this is the opposite view. So I also went to the Solar Heat Worldwide Report with the data for 2024. But in this case, I looked to the other side. So I tried to find where were the SHIP applications, so the solar heat for industrial process applications for PVT. And what I noticed is that by the end of 2024, there was a cumulative installed area above 1,600,000 square meters. 2/3 of these area corresponded to water collectors and 1/3 to air collectors. And the vast majority of these collectors, namely the water collectors, are uncovered collectors. So more than 90% are uncovered collectors, and only 8% are covered collectors. And also, for the concentrated PVT collectors, they represented less than 0.2% of the cumulative installed area. And if we were looking here for the different applications, looking for the solar heat, we can see that directly identified as solar heat for industrial applications, only 2% of the PVT systems installed worldwide in 2024. Of course, that we need to take some care with this data because there are 26% of installations, or better said, of area installed where no application has been identified. So maybe this value is a little bit higher. Nevertheless, what is important to notice is that this is a very low area of installed. So why is this? Well, there is a reason why this is happening, and this happens for us to understand it. We just need to look to the efficiency curves of existing PVTs. And we can start by looking to thermal efficiencies. And we can see that the thermal efficiencies of some selected PVT collectors are, they drop very fast when we are increasing the temperature level. So this is the case, of course, for unglazed collectors. Glazed collectors have higher thermal efficiencies for a given operating temperature. And if we go to concentrated systems, for example, this red curve here is a concentrated system, we see the effect of concentration increasing the efficiency for higher temperatures. Nevertheless, in all of these cases, the operating temperatures will be very low. As you can see here, we are talking about average fluid medium temperatures. If we consider typical ambient temperatures of 20-25 degrees, we are reaching here zero efficiency below 60 degrees C of operating temperature.
Wow.
There is.
Sorry to interrupt you. This is timekeeping. Just like if you can finalize in 1 minute. Sorry about that.
Oh, okay. Yeah.
Thank you.
Sorry about that. Well, basically the problem is that we also have an inverse relationship with temperature and electric efficiency, where we have, as we increase the operating temperature, we will increase the PV cell temperature, and of course we will get lower electric efficiencies. So that's why current commercial collectors target low temperature applications, or they are integrated with other technologies as PV. We can improve, and we need to develop cost-effective PVT collectors for industrial applications. This can be done, for example, using high vacuum enclosures, using concentrators, both imaging and non-imaging, together with spectral splitters, and so on. There are some examples in the literature, not so many, showing how, for example, using high vacuum, we can have high temperatures at operating temperatures of high efficiencies at operating temperatures of 100 degrees C, how we can increase electric efficiencies by using nanofluids to improve the heat transfer from the absorber, and so on. So I will just conclude even showing that the integration points for PVT systems in industries are very similar to the integration points for typical solar thermal systems, but we should target the low temperature processes, like preheating of makeup water, heating the return line, so condensates heating, and so on. So I'm just going to show two examples, two case studies that we are analyzing on the PVT4EU project. One is dealing precisely with boiler feed water preheating. So we are collaborating with a large multinational company of the food and beverage sector to analyze the integration of PVT collectors in the energy system of a canned food production plant. This facility uses natural gas boilers to produce superheated steam for process heating in processes such as thawing, cooking, cleaning, and sterilization. And so part of the steam that is used in these processes is recovered as condensate and gathered in a condensate tank, where makeup water is also added. And what we are doing is we are preheating this mix of makeup water and condensate tank before it is pumped to the steam boiler, therefore reducing the fuel consumption of the gas steam boiler existing in this plant. Another application is with regarding cooling, and in this case, what we are doing in the same plant is we are studying here a different perspective, which is we are producing electricity with our PVTs, and we have some, let's call it waste heat from the PVT, and we are using this heat to drive an absorption chiller. Or an adsorption chiller. They can be driven by hot water at temperatures below 100 degrees C. And in this case, we are using this cooled water to cool the food cans after the sterilization process that occurs within autoclaves. And this reduces the time required to cool the cans, and so we can have more production cycles within the production line, and we can increase the production. So we are working on these studies. We will hopefully publish and disseminate more about these results in the next months. And well, I'm looking forward for your questions. Thank you.
Thank you very much, Joao, about the presentation and regarding sharing the information about what we're doing on industry applications with the collectors that we're developing within PVT4EU. I know that we carry on some delays, so I apologize for that. But so I will give now the floor to Marcus. Actually, I think that he's quite ready now to start. So Marcus, the floor is yours.
Thank you very much, and thank you for bringing the industry together like this. I agree we're a little bit delayed, so I have decided to make a little bit shorter presentation for the one who needs to stay to the schedule. And then there will be a good cliffhanger, 3-4 minutes with a video and a customer case for the ones who have time and possibilities. So I will try to catch up with the time schedule, Ivan. Yeah, and my name is Marcus. I represent Dual Sun, and I hope you can see my screen good now.
Yes, everything is good, Mark.
That's great. And Dual Sun is a French producer of PVTs, and was actually the first one to get the Solar Key mark. And since then, there have been many iterations, and the product line today looks like this: a finned version where we use the PVT as sole source for heat pumps. We have a non-finned, non-isolated version, which is the standard for the Nordics in combination with heat pumps. We do also have an isolated version for higher temperatures, but it's actually not applicable in the Nordics, and I will come back to that. And then we're also supplier of PV panels, since it's often a combination between PVT and PV. This is a slide we have developed, and we would like to share it with all of you if you find it useful. But for us, it has helped a lot to explain to customers why it's possible to extract 6 to 8 times more energy from the rooftops with PVT than PV. So we have the PV part, we have the additional electricity because of the cooling, and we have the heat losses taken care of by the heat exchanger. That's the image most people have of PVT. And then they're really surprised when we add up with the aerothermal part, that we can use the PVT as a heat exchanger, like we have air to water heat pumps. So, and in this case, we hit 6 to 8 times more, some cases even more, 10 to 12. But important is that in the Nordics, we have a lot of heat pumps and we have cold climate. So that gives different solutions than we have seen earlier today from Spain, and also different solutions from our colleagues in France. So we use PVT in the Nordic countries in 3 applications, 3 main applications. One is as a sole source for heat pumps, liquid to water heat pumps, what we call PVT heat pump. Most of the PVTs are sold to combination with boreholes, existing solutions, or new building where we need to optimize the COP. The final option is where we have limited plot areas and can't establish a geothermal system, but with a recharge we can make it more dense and actually enable more geothermal solutions where it's not possible. So those are the 3 areas we use PVT in the Nordics. My presentation is about customer value and accept not only cost reduction and resilience. A lot of focus with the EU taxonomy is now about energy labeling, and to have a good labeling is important to have green loans. So here is 2 new building projects we have done. The one here is a 10-floor building to Skanska, big construction company, and it's actually a net zero solution. This area, one of the areas is PVT, and the rest is PV, and you have 10 boreholes and heat pump. Another example is what we call PVT source heat pump. In this case, it's a building in Lund, it's close to Malmö, south of Sweden, where district heating wasn't clean enough to get the necessary labeling. But with a local solution with PVT directly to a liquid water heat pump, it was possible to raise the energy class from C to A. And that was done in cooperation with the district heating company. So it's really good example that the technologies can coexist. Maybe I should mention that the guys at the district heating company had a background as geothermal energy guys. That helped probably, but it showed it's possible. This is a case, actual case, and double up with a customer, property owner was mentioned. It's the same property owner in Stockholm. It's an old multi-family house built in 1940. And the plot is very small, so it's not possible to make a geothermal system. But with PVT, we can do it and reduce the diameter from 20 down to 13 meters. And this customer has made a lot already. They changed windows, they improved ventilation system, so they are actually on a D level. So what are the options? Yeah, they can add PV, reduce the purchased energy with 3%, or they can have a PVT source heat pump, 33%. But since it's an old building with a high energy demand for heating, we need to go with a ground source geothermal system, and then we can reduce to 71 purchase energy. And if we look at the weighted energy, which is the basis for the energy labeling, it looks like this. Today, they are on a D level. With PV, they will still be on a D level. With a PVT source heat pump, they will reach C, and in this case, a ground source heat pump and geothermal boreholes, they will reach B. And B is important because then you can get the green loans. So for the ones who need to stay to the schedule, it's 11:33. And for the others, we have a 3-minute video, a customer case, very well documented over 22 years with a system from Siemens and Schneider documenting all energy. The customer documented all investments. So it's a really strong case, well documented about an energy journey over 22 years from class G up to B. So I will start this video now.
Used for heating and hot water. I want to tell you about Enwell's 22-year-long and successful collaboration with the Heinehem Homeowners Association to reach their goal, phasing out the 170 cubic meters of oil used for heating and hot water, which today would have meant an energy class G rating. Today, oil use is almost zero, and the houses in the area comfortably meet energy class B standards, enabling green financing mortgages and low cost for heating and hot tap water for the residents, in addition to the significant environmental benefits. Welcome to Heinehem Heating Center. Come inside. The heat pumps were sized according to the design rules of the time, which required 50% capacity power coverage to achieve 80% energy coverage. Back then, we installed 440 kilowatt heat pumps and drilled 22 boreholes, a total of 4,400 meters. That was what we did in stage 1. Everyone was satisfied, us as contractors Enwell and our customer Heinehem. This laid the foundation for continued cooperation. Everyone was motivated to continue fighting oil consumption. To increase the temperature in the boreholes, and thus improve the performance of the heat pumps. A first solar hybrid system was installed on the heating centre's roof in 2013. But solar hybrid technology has also advanced, so in 2021, DualSun's more efficient hybrid panels were chosen, providing more heat and electricity to the system, further improving the energy balance and performance. From the very start, a monitoring system was installed to control the system and collect operational data. The roof, with its 94 hybrid panels, produces about 160,000 kilowatt-hours per year, which means about 1,700 kilowatt-hours per panel annually. That's 6 times more energy per square meter than regular solar panels. The Homeowners Association has made many investments over the years, but since the investments were self-financed, the monthly fees for members have remained at the same low level for many years, despite energy crises and inflation. For residential buildings, heating and hot water are the major operating costs, not electricity. With hybrid panels, we use roof space 6 times more efficiently than with solar panels and can address all energy needs. Thanks to solar and geothermal energy, it has been possible to phase out almost all oil consumption while achieving very low operating costs. With DualSun's efficient, well-proven and robust hybrid panels, we can help you towards a sustainable and cost-efficient future.
So that's it. Thank you very much.
Thank you very much, Marcus, for the very good presentation. I think that every time also that I see this video is quite exciting. I remember seeing it first in the Energy Mesa, where we met like a couple of months ago, where you also give a lecture about the integration of and the integration schemes that you have with DualSun and also some other companies. So I would like to thank all of the speakers for this first session, in a second session regarding system integration and applications. In this new section of the workshop, we are going to be addressing modeling techniques for PVT systems, and when we're going through collector level, system level modeling. And the first speaker, it's going to be Chandan Pandey, a colleague from the Imperial College London that I'm glad to present today.
Yes, can you see my screen, Ivan?
Yes, it's visible now. Yes.
Okay, yeah. Hi everyone. My name is Dr. Chandan Pandey, and I'm a research associate in the Department of Chemical Engineering at Imperial College London. And I'm going to present some insights on design of hybrid PVT collectors, and it will be mostly on the collector side, that is component side. Okay, so the motivation is like, if you look at the solar cells, they have like conversion efficiency of 15 to 20%, and the rest goes as waste heat. And the idea is to extract that waste heat using a thermal absorber, and this can be achieved with the help of a PVT collector. 1 minute, sorry. So the figure that you see here is a PV cell and a solar thermal absorber. So these, like if you put them individually, they'll acquire some space. And if you combine them together, they form a PVT collector, and roughly you save 50% of the rooftop space, which is a premium in apartments or buildings. So this is the main motivation why PVT collectors are important. And like Ivan said, Ivan presented in the morning session. So Europe hosts like 64% of the world PVT collector area, and globally the area is 1.6 million square that has been in operation, and this translates to roughly 0.2 metric ton of carbon dioxide emission, mitigation of 0.2 metric ton of carbon dioxide emission per year. And if you look at different process heating industries, like dairy, textile, chemical, food, paper. So they have a requirement of hot water in the range of 60 to 80 degrees. And PVT is a tailor-made solution for this, because PVTs, they generally if you use a glazed PVT collector, you can always achieve those high temperatures. The aim of my presentation is to give an insight on design of hybrid PVT collectors, and the objectives are like I'll give insights on 0D modeling, 1D modeling, and 3D modeling. Moving to next slide. So this is a typical characteristic curve of a PVT of solar thermal and PVT collectors. The black line that you see is a typical solar thermal unglazed solar thermal collector, unglazed, and the dotted line that you see is a typical efficiency curve of a unglazed PVT collector, and this is the efficiency curve of a typical glazed PVT collector. Well, this is the point that you see here is the maximum thermal efficiency point, and this is the optical loss that you have from the collector. So our aim is to reduce these optical losses as much as possible, so that we can generate more thermal energy from the collector. And second thing is you see the pink area, that is the thermal loss from the collector at different operating temperatures. That means when the mean temperature of the collector is increasing, the losses from the collector are also increasing. So our aim is to reduce this as much as possible, which can be achieved by using a glazed PVT collector. You can see when like this is it is not a fair comparison, but you can see here, this is the characteristic curve of an unglazed PVT collector, and this is the characteristic curve of a glazed PVT collector. So when you have a glazed PVT collector, you tend to, reduce or suppress the convective and radiative losses, and you tend to increase the operating temperature limits of the collector. So these are the, characteristic curve equations. These are obtained by thorough testing of the collector using ISO or IEC standards. And you can use these equations directly to estimate the outlet temperature of the collector. So I call this a black box model, where you don't know what are the components involved, and still you manage to estimate the outlet temperature of the collector using the set of equations that you have here. This is the recent paper that we published in renewable energy, and we have specified, or we have specified how we can use these equations to estimate the outlet temperature. You can, if you're interested, you can look into this. Okay. So in order to estimate the performance of the PVT collector, it is important for this model that we have these characteristic curve equations. If a user says, okay, I'm more interested in designing my own collector, and I want to design each and every component, the next steps, then you need to move into more detailed modeling, which is 1D numerical modeling. In 1D numerical modeling, you have the flexibility. It's no, the collector is no more a black box. It is more of a components that you are designing that you are using in your collector. And the numerical modeling approach, you solve the energy balance equation for each layers. For example, the radiation comes into the falls onto the solar cell. The solar cells, they generate heat, and then it transfers heat. The solar cells will transfer heat to the PV glass and the aluminum sheet, and from the aluminum sheet, it is radiated to the ambient. It is radiated to the sky and ambient. So you need to write energy balance equation for each components. And then from the aluminum sheet, the heat is transferred to the tubes and to the ambient. If you have a good insulation, maybe you can retain those heat. So yeah. So these are the set of equations that you can use in order to estimate the thermal performance of the collector. I'll not go deep into it. And if you want, you can, you can refer this reference here. So these equations, they are ordinary differential equations. These differential equations can be solved. Again, these equations that you see here are for steady state dynamic conditions. And the input that you need to provide are solar radiation, wind speed, ambient temperature, inlet water temperature. And then you can, write your own code using MATLAB or Python or any platform which you're convenient to work with. And then the outputs that you get are glass, solar cell, aluminum plate, back plate, and outlet water temperature. Well, this is again a dynamic condition where everything is a function of time. Like your solar radiation is a function of time. All the temperatures that you obtain are a function of time, and then the time steps are also equally important while modeling these kind of systems. If you want to develop a situation where there's the collector has achieved steady state, then you need to set these equations. You need to set the capacity term to 0, and then it becomes a nonlinear algebraic equation that requires the same input, and you'll get these output, that is glass, solar cell, aluminum plate, black plate, as the output. Well, the next steps, the limitations of 1D numerical modeling is you cannot see how the temperature distribution actually looks like in the collector, and they might not be that accurate. So in order to improve the accuracy of the simulation, what you can do is you can develop a 3D model. 3D modeling can be done in various ways. One of them is like you write your own code. Second is using a commercially available software. For example, I use COMSOL a lot here. You can also use Fluent. And in the platform, whichever you're using, for example, COMSOL or Fluent, you need to design your collector. I mean, you need to design the collector in the sense you need to draw the different components. For example, I have drawn unglazed PVT collector here and a glazed PVT collector here. And you can then you need to add physics, which has to be coupled with physics, which includes your heat transfer and fluid mechanics. And these needs to be coupled because they cannot work separately. It has to be coupled in order to see the performance of the collector. Once the physics has been added, you need to add material properties. For example, I have used these material properties based on one of my papers. If you're designing your own collector, you can go to any, you can choose any material, and then you need to give boundary conditions, and then do the meshing and solve the governing equations and get output. So these are sample or these are the validation results for one of my papers that was published in Solar Energy back in 2021. So these models, they perform really well with relative error under 5%. So in my case, I got 5%. If you design it in a more better way, then these errors can further reduce. And this will give you a holistic picture of how the temperature distribution looks like in your collector. So in conclusion, I'd say there are different types of collector, glazed, unglazed. So it depends on the user what you want. Whether you want more heat, then you need to go with a glazed PVT collector. If you want to, if you want more electrical output, you need to go with unglazed PVT collector. 0D models, they can estimate thermal performance, but again, it's a black box. You're not designing anything. Somebody else has designed it. You're just using the equations. In 1D, you design your own collector. In 3D, you get more holistic view of how the temperature distribution looks like. And so here at Imperial, we are working. One of the challenges that we have found with the conventional PVT collector is the coupled heat and electrical output. That means if you want to generate high grade of thermal output, you need to compromise on the electrical part. So we are working on design of spectral splitting PVT collectors, where we try to decouple the electrical and thermal performance so that both of them can operate independently, and we can decouple them, and we can achieve even higher temperatures from the thermal absorber without affecting the electrical performance. Thank you. I'm happy to take any question if you have.
Thank you very much, Chandan, for the presentation. And yeah, sadly, we are not opening to questions in this regard, but I see that the chat is quite active, so it is good to have that interaction there. And yeah, regarding also this last part that you mentioned, the future developments, which is something that we're going to be also addressing in later stages of the workshop. I have always mentioned that PVT is a two-pieces cake, right? If you want to increase one, you have to compromise the other one,
Yes,
right?
exactly.
In this case, with this new technology, you can also try to decouple this intrinsic relationship between both, right? So again, thank you very much, Chandan, for sharing your insights and regarding modeling collectors and how to design them as well.
Thank you, Ivan.
With that,
Ivan, sorry,
Ivan,
but
I can't hear you.
I cannot hear you.
Oh yeah, sorry. I think I muted myself. So fine, I was giving the floor to you. So I see that you're already prepared. So yeah, you can start with your presentation.
Okay, thank you. Although I didn't hear you, but I know what you want to see, so I prepared.
Great.
So I think you can see my screen, right?
Yes, we can see it.
Is it good, or it's like a full screen or not?
It's not actually, it is full screen, but I think that is because you have a bigger screen that is a bit small, but I think that we could manage to see it. Yeah, then it's better, much better.
It's better now?
Yes, exactly.
Okay, good. Thank you. Thank you. Thank you, Ivan, for this invitation to share some of my research. The topic of my presentation is on software tools for PVT simulation. So the original title for the presentation is for system simulation. I deleted the system because some of the CFD simulations are not possible or not feasible for system simulation. It is mainly for component calculations. So I will start with a comparison of the two tools. The two tools, mainly CFD, that is computational fluid dynamics, and this is mainly for detailed component calculation or modeling. Well, there's another tool. I want to have my presenter. Right? Yes, and there's another group of tools which is for system simulation, like Transys, Polyson, or Modelica. So if we compare these two groups of tools, CFD, of course, it is very detailed. It is very advanced. You can make calculations of heat transfer, mass transfer, a lot of things you can do. But of course, for that, it requires you to have a detailed model of your collector. For example, you have to to model the flow channels. You have to, if you want to model air collector, you have to also to have the whole channel included in your domain. So all this will take time, and then also like CFD simulations typically requires a higher computational cost. It takes longer time to do the calculation. So therefore, typically CFD simulation is used for component optimization and component design. While Transys, in the other hand, is like a low setup time and low computational cost, and it is aimed for system simulation. Of course, a good way is that we could combine these two tools. We use CFD to refine the component model for Transys. Therefore, we can have increase the accuracy of the system simulation. So let's first have a look at CFD modeling of PVTs. At this graph, I just had this figure today. It shows the scientific publications of CFD modeling of PVTs. You can see that this is a number of publications in our database per year. You can see that starting from 1970s, almost very limited CFD simulation of PVTs. One reason is that these PVTs is not that popular. Another reason is that the computational power for computers is not strong enough for high performance computing. But after year 2000, you can see that increase of publications of CFD modeling of PVTs. So it is becoming more and more popular. And what is CFD? I don't know what is the knowledge of CFD from an audience. I just want to give a brief introduction of the CFD as a tool. So CFD is the science of predicting fluid flow, heat transfer, and mass transfer by solving these mathematical equations. And these equations, we call it governing equations. They represent the physical laws, and all these processes is done by numerical processes. So this is what is CFD. So how does CFD work? CFD work, let's give you the idea. First, of course, I base this method of fluent on finite volume method, but there are also other group of methods use finite element method. So the principle for CFD is that first, the domain. If you want to make a calculation of air collector, you have to draw all the flow channels, and this is first we call it to create generate a domain, and then you have to discretize the domain into many small control volumes, and in each of the control volume, and then you have the governing equations like mass equation, momentum, energy, and other equations has to be discretized in each of the control volume. In the end, you have a large number of equations. All these equations will be solved by iteration using the numerical method. Then you have all the parameters of your domain. And this is a CFD modeling overview. As I said, if you want to make a calculation of PVT collectors, first you have to draw it. You have to draw the collector, the geometry of the collector in the program, and then you have to generate the mesh. This is what we call it the discretize the domain. After that, you need to set up your equations. It depends on the physical model of your case. You include turbulence or not, radiation, phase change, or other physical models. You need also to define the material properties for the air, for the collector material if needed, and boundary conditions, and also initial condition. And then you make the calculation afterwards. That is the post processing. And this is an overview of the available CFD packages. You can see that there's ANSYS Fluent, which is the most popularly used CFD codes. And there are also other CFD programs from ANSYS. So they are from the same company. There's also StarCD and SM from Flow3D, Phoenix, and OpenCFD that is open source and free based on Linux. There's also CAMSO. I didn't include that because CAMSO, of course, you can also do CFD calculations, but it's not specialized in CFD simulation. But these codes, they are specialized in CFD calculations. So this is an overview of this ANSYS Workbench overview. As I said, ANSYS, that is the most popular CFD software, and the latest version of the program is the 2025 R2. Almost they issue a version twice a year. You can see that this is the interface for ANSYS, and it's a combination of a lot of the programs or packages from ANSYS from the company. For example, the matching part and the geometry part and design modeler, that is where you create the geometry and you make the calculations, use Fluent. It also includes the package for CFD. And the good news that if you are a student and if you want to learn the program, you actually can download the program for free. You have the limitation of 500,000 cells, but you can get access to all the functions of the program. And then, we should not limit it to CFD because CFD cannot do anything because for system simulation, it is not possible. If you want to do system simulation, you have to use Transys or Modelica or Polyson. And this is like a two component used at DTU, used by my colleague, Mark. So I borrowed some of the slides from him. These are the two components for PVT. Like PVT, one is PVT in one type. So one transist type, both have the PV part and thermal part. And this model, that is, you can see that it considers effect of air speed and long wave radiation and to sky and collector capacity and condensation effect, etc. And there's another component which we use that is composed of two components. The one part is for the PV part, other part for the thermal part. You can see that you have the PV part, the thermal part. This you can of course simulate together the performance of the PVT. Here at DTU, we have a lab. We can test 8 systems parallel. And some years ago, we tested PVT water heating system. And this PVT water heating systems with a heat pump. And we have like 3 square meters of PVT collectors. You can see that these PVT collectors can be used to charge a tank. We call it cold tank. And if the temperature is higher enough, we can also use it to charge the hot water tank, which we call it hot tank. And then, of course, if most of the time the PVT is not the temperature from PVT is not high enough, then we use a heat pump. So the heat pump use the cold tank as heat source, and then rise the temperature, and then hot water is stored in this hot tank, and hot water will be taken from this hot water tank for the building. You can see that this is the test, the 3 square meter PVT collector, and this is the system with the heat pump, and this is the 2 tank. And so we have made a test of this system both winter and summer, and in quite a long time. And besides test, we also made system simulation, as I mentioned, use a component in Transys, and this is the system layout in Transys. You can see that we have the PVT collectors, one component, and it is connected to the domestic hot water tank and also the cold tank. And for this heat pump over here is the low temperature side is connected to the cold tank, and the high temperature side is connected to the domestic hot water tank. And then there's a draw off from the domestic hot water tank. And then we compared with the performance of the system. This is the data taken from year 2017, from August to December. Quite some months, you can see that this is the daily PVT output and the electric output and the thermal output. You can see the comparison of this model with the measurement are actually quite good. I don't have time to put more information on this. If you are interested, please have a look at the publication of Mark. That is, the link is given over here. And then besides lab tests, we also had done field testing and also safety and transit simulations. And we made the measurement from the real world, from the installations in single-family houses. And we also built the transit model for it. And this is a system layout as the PVT collectors connect to the heat pump with a domestic hot water tank integrated in this one component. And the system can also provide space heating because it's a heat pump. And then the PVT collectors act as like heat source for the heat pump. And this is like transit model. You can see that in this model, it used the two-component system. And for that, this is like the heat pump where we can provide hot water and space heating for the single-family houses. And we use the measurement from the field test and validate transit model. And then we use the validate transit model to do like a location for different locations to see the performance and so on. If you are interested, you can also have a look at this conference paper. And the Polyson, we do also like use Polyson to do the simulation. And this is done in this project in Denmark. It's an ITP project funded by Danish Energy Agency. And this is how the system looks like. And this is like a PVT panel. And we have a heat pump. We have the hot water tank and space heating tank connected to the heating loop. And the aim for this project is that we want to see how the yearly performance affected by the properties of the collector, like for example, optic efficiency, heat loss coefficient, and how can these low cost, low performing panels work well in a PVT system. So this project is done. And then we are, as mentioned, we are part of it.
Sorry to interrupt you.
Yes.
Will you be able to finalize in 1 minute? We are already over time. Thank you very much.
This is my last slide. Yes, and we have this like part of this PVT for EU project, where this investigation was carried out. Like the drafted PVT models. This is the one model PVT system for heating of swimming pool, and this is like PVT system for connecting with the borehole heat storage. So we can use that to heat the low energy buildings. So I think that's all from my side. I'm glad to hear the work from DTU. Thank you.
Thanks. Thank you very much, Fan, for the presentation and for introducing how we can model PVT systems, and also how validation is quite crucial in order for us to make sure that the models that we have developed are reliable, let's say. Also, just like a quick fact, as far as I know, the first record that, as I mentioned, as far as I know, recorded paper or published paper on PVTs was back on the 70s, 78 to be more precise. Maybe more people here knows better than me, but it was presented in a IEEE conference in the 78 by Kern and Russell, and it was the first introduction of PVT, at least at research level and also at communication level. So that was also nice to see regarding the graph that you share, Fan.
Yeah, nice.
Just a quick tip. Thank you very much. Then we will move forward with the last presentation of this section, and it's going to be again Francisco. So Francisco, the floor is yours.
Okay, so thank you, Ben, again for the introduction. So we'll talk a little bit about system level modeling for integrated PVT systems. And it's great that Fan gave a general overview of system modeling and what are the different tools, because then I can jump straight to an example that I have on like a research project that we have been working on. So again, a PVT heat pump concepts that I was mentioning before. So for this example that I will show now, I will focus on the series regenerative configuration. So using the PVT both to act as the source of the heat pump, but also to regenerate the ground. So this is like a PVT plus ground source heat pump system model that was developed by Nelson during his PhD, and we are still using. So it might look a bit confusing there, but I guess you're all familiar with transit probably. But then here you have the PVT loop, then connected through like a heat exchanger with the borehole loop. Then you have the heat pump there in the middle that I won't open because it's a lot of components in there in that macro. And then you have the space heating and domestic hot water demand on this side. So the building loads are being simulated in transits as well. So in the original model that Nelson developed, we were using a theoretical model for the PVT type 560. And then it had all these parameters, right? Like collector length and width, absorber plate thickness, absorber thermal conductivity, number of tubes, the bond width, bond thermal conductivity. So these are all things that probably you know if you're the one manufacturing or like designing your PVT, right? So it should be, you should be able to use this model, and especially if you're doing, for example, CFD modeling of a special like particular component, and then you want to apply it in CFD simulations. But then when I started my PhDs, we were working with the name of the project was Smart Sol, and it had like several research questions, but I tried to narrow it down to the simple one: what is the best techno-economic PVT design for ground source heat pump integration? So we had a lot of CFD modeling using COMSOL as well, looking at different designs, different materials, adding fins, for example, adding forced convection. Then we did some PVT collector prototyping and testing. We're using the ISO standard equation to derive the coefficients. And then we moved to the system model. So all what we learned at the component level, we wanted to apply it at the system level. But then if we wanted to use type 560, it would require us to like input all those parameters, which would take some time. And also, if, for example, we wanted to benchmark it against commercially available products, how do we know exactly how the PVTs are being manufactured and all these properties that I was mentioning before? So then, as Fan was mentioning, we got in touch with a researcher from ISFH who also came to visit us, and they developed at ISFH a type 203, which is based, it's an empirical model, not a theoretical one. So what you need to input are these parameters: the zero loss efficiency, the independence, heat loss coefficient. So all these empirical coefficients. So it makes it easier to model different collector designs, which was what we were trying to do. And then one good thing about this empirical model is that you can get the coefficients from different sources. For example, in our case, we have a testing facility on the roof of the energy technology department. So we could derive them through our own testing. We also used numerical model. So you can do functional multiphysics and sysfluent as if you were testing them, and then derive the coefficients as well using linear multivariable regression analysis, which we also did. And then we had our own designs, but we also maybe wanted to compare them with some other designs that are commercially available. So then you can also go to some like the Solar Kimmer certification webpage, for example. And this is an example from DualSun, and you get all the coefficients for the collectors that have been tested and certified. So it's quite easy to, for example, if you were designing your system and you want to see which collector is better for your system, you can just find this spec sheet, look at the coefficients, use them in the model, and then of course, there are some assumptions that you will need to make, but most of the things you need for that model are there. And then for the heat pump, because we are working a lot with PVT integration with the heat pump, we use a black box model. So it's a three-dimensional interpolation of a performance map, which you get from the manufacturing. We basically have the source temperature, the supply temperature, And for every combination of two, you have like a compressor speed as well. And then from this performance map, you get the electricity demand of the heat pump and also the heat rate, so the heat supply. And the supply temperature, you get it like for every building, there's like an equation depending on how old it is and the materials. You can use this equation for the supply temperature based on certain coefficients and the ambient temperature. All this is described in Nelson's paper from 2019. And then now I thought it would be interesting to present a new study that is currently under review, which is hopefully my last paper of my PhD. So it's called Cutting Peaks and Costs, Technographic Design Guidelines for Solar PVT and Ground Source Heat Pumps in Land-Constrained Multifamily Buildings. So the land-constrained part is because when Nelson was working with PVT ground source heat pumps, he found that the biggest potential for PVT wasn't in like new systems, but for example, the application that was mentioned before, rescuing frozen boreholes or using PVT to support shorter boreholes in areas where there's not enough space to drill like a fully sized borehole field. And usually the systems would be designed for a fully sized ground source heat pump and optimized for that system, and then evaluating the performance for a reduced size. So what we did in this project was to start from an undersized borehole field and sort of optimize the PVT system design for these undersized borehole. So these were the research questions, but they can be summarized as how should we design these PVT ground source heat pump systems, and also we were trying to look at what's the potential to reduce the peak power demand, something that's getting more and more important also. Not just, we don't want to reduce just energy consumption, electricity consumption, but also the power during peak demand periods. And then we were looking at different pricing strategies and also comparing it with other heating alternatives. And this is sort of the methodology that we followed, looking at collector type and array size, then where to place the heat exchanger, different cut-in and cut-out temperatures, then what flow rate should we use? Should we use a fixed or a delta T controlled flow rate? So do we vary the flow rate or do we use a fixed flow rate to keep Then going back to the array sizing again, and then using comparing what happens if we have an energy or a capacity pricing tariff, and then different pricing scenarios. Is the target building? I would just summarize it in it's a multifamily house. Then you'll probably share these slides, Ivan, so you can look at the target building there. I want to go fast through these slides so we can go too much time. And these were some of the PVTs that we were testing and comparing. The sheet and tube, a box channel polypropylene, then a thinned tube, and then a box channel aluminum with 20 millimeter fins, because we also wanted, as part of my PhD of trying to find what PVTs to use for these applications, we wanted to compare different PVT designs. And these were like some of the first results that we got. The figure on the left, you have SPF, like seasonal performance factor, and the total life cycle cost. So you can see for like SPF, of course, the more PVTs you add, the better it gets the performance of the system. Yeah, the gains lower as you go up in array size. And then when you look at total life cycle cost, there seems to be like an optimum at around 48 or 60 square meters. After that, cost is expensive. And then on the right side of the screen, you have a comparison for every month for the first year, the thermal energy output of the different PVTs. And something interesting that you can see there in this figure, if you look at it in detail, is that there are some PVTs that perform better than others because of the coefficients of the design characteristics that I was mentioning before. There are some PVTs that perform better than others in certain months, and some that, it changes. It's not that one PVT performs better than all the others for every month of the year. So this is why it's important to keep in mind the design characteristics of the PVTs. Then another thing we looked at, as I was mentioning, was the location of the heat exchanger. So where to place it, like between, after the heat pump and before the borehole, so between the heat pump and the borehole, or between the borehole and the heat pump. So, and then what we noticed here is that there was a very little difference. So, yeah, I won't go into detail with this one, but yeah, the seasonal performance factor and the cost of the system didn't change much depending on where you place the heat exchange. Then flow rate, this is a very important one, and it's also, it depends on the application that you are using, because for example, for a fully sized borehole field, the optimum flow rate was much lower than with an undersized borehole field, because there's much more like energy to save here in this kind of system. And you can see that there's like a much, the black line are the net savings, and you can see that there's a sort of maximum net savings at around 80 liters per hour per square meter. And then you look at the graph to the right, that's also where you get the minimum total life cycle cost of the system. And yeah, I have 2 slides left. So this one is also the first graph that I showed about PVT collector type and array size, with some like the settings, like the parameters that we were using here were for like a fully sized, like the control strategy was what we got from the fully sized borehole field. But then after performing all these steps, this optimization, we did another iteration to find the optimum PVT collector type and array size. And we can see that the optimum moved a little bit to the right towards a bit larger PVT array sizes. But what we noticed here is that the difference in total life cycle cost between the best performing design and the worst performing design was quite low, around 2%. And then also the effect on peak power. We saw that adding PVTs to this undersized borehole field from 24 square meters of PVT onwards, it could reduce peak power demand by around like 8 to 10%, which is quite important. And another argument in favor of PVT with ground heat pumps, the potential to reduce peak power demand. Yeah, hopefully the paper will be published soon, and you will be able to read all the details. But I wanted to give like like an example on how to apply a system modeling of PVT collectors. Yeah, thank you. That was it.
Thank you, Francisco, for the interesting presentation, and also that give us some ideas regarding the importance of doing system level modeling, and also how important it is to couple that with the thermal coefficients that we could either obtain experimentally or theoretically, as you clearly mentioned as well. And also for sharing the experience that you have in the system modeling in your area, which is basically with ground source heat pumps and coupling with PVTs, with heat pumps, sorry. So thank you very much again also for the people that join us. With that, we close the third section of the workshop, and now it's time for lunch. I'll give the floor to our folks in Lenec.
So hello everybody, my name is Jorge Facão. I'm working in Portugal in LNG. So I'm working in a solar energy laboratory. It's a laboratory for testing solar systems and components, let's say collectors, systems with thermosiphons or tanks, and of course some PVT collectors. So in the framework of the PVT4OU project, we intend to develop two prototypes of a PVT collectors. One is a whisk collector, and the other one is a symmetric CPC collector. So the whisk collector could be used for heat pump source, for heating water or swimming pools or domestic hot water and space heating, and the CPC could be used for process heating. So these figures present the application temperature of both prototypes we intend to use. So in order to evaluate the thermal performance, there are two tests. One is to evaluate the thermal performance, and another one is to evaluate the electricity produced by the PV cells. So my colleague afterwards, Carlos Rodrigues, will talk a lot about the electricity produced by the PVT. So according to the standard, there are no standard specific for testing PVT collectors. So the thermal performance could be tested according to ISO 9806. So this is the standard for testing solar collectors, and could be used also for testing PVT collectors. So in this basis, solar key mark certification of PVT collectors is possible by applying specific rules for testing collectors. So according to this standard, the thermal performance of a PVT collectors must be tested with a synchronous thermal and electrical generation under maximum power point conditions. So during the thermal performance, the PV could be connected with the MPP conditions, and if you test the reliability, so the durability of the PVT collectors, the PV is not in the generation conditions. So the thermal performance can be assessed by this equation. So this equation, the first equation is the power from the collector. So you measure the flow rate, the specific heat of the fluid, and the outlet temperature. Then this gives the heat produced by the PV, by the PVT. And then there are equations according to the quasi-dynamic test, which is a fitting of this power according to the measured variables. Let's say the temperature, the irradiance, the wind velocity, and so on. And then with the power measured by the collector, we can evaluate the parameters that fitting this equation. So another parameter that is important to evaluate during the thermal performance is the incidence angle modifier. In order to adjust these parameters, there are two methodologies. One is linear and another one is non-linear. According to the standard, there are an equation presented below. This equation is a question that is a non-linear fitting of the parameters. So if the collector operates below ambient temperature and below dew point temperature, there are a condensation risk on the PVT. This is very important in the whisk collector because the whisk collector operates below ambient temperature when it is operated with the heat pump, for example. And if the collector operates below ambient temperature, there are some modifications on the equation showed before, and there are about 5 modifications in the equations. So the last modification is a term related with the rain. So if there are rain as well, there are another parameter that is A11 that is be added to the equations. And there are, of course, some modifications related with the condensation and, of course, with the long wave radiation near the collector. So regarding the facility to test the PVT, so this is more or less the figure that is presented in the standard in the ISO 9806. So you measure the ambient, the inlet and outlet temperature of the collector, and the ambient is the air temperature. We measure as well the relative humidity and rain. We measure the flow rate of the fluid, the wind velocity, the solar radiance. The solar radiance is measured by the piezometer, a pyranometer, and imperialometer in order to measure the some components of the radiance, and of course the wind velocity with the anemometer. In order to measure the PV, the electricity produced by the PV, use a power meter that my colleague will talk a little bit about that measurement. In this project, we intend also to measure the photovoltaic cells and the absorber temperature, especially in the wish collector. So the quasi-dynamic test, this test consists of 4 or 5 test sequences. So the number of days, it depends on the weather conditions on test site. So the data is recorded, should contain data equivalent for all important normal operations conditions and no variability in dynamic range to give the coupled collector parameters. This is done by varying the LED temperature of the collector in its horizon range. So usually we measure the performance of the collector from the ambient temperature until the maximum operation temperature of the collector. So the minimum length of the test sequence shall be at 3 hours. These hours do not need to be consecutive, and the test can consist of several non-consecutive parts within a minimum duration of 30 minutes. So there are 5 sequences. So the first sequence is the day type 1. It is to evaluate the thermal performance with a temperature near the ambient temperature and with the sky clear. The day 2 is a day with a cloudy day, and the temperature could be near the operation temperature or near the ambient temperature. The day 3 is a day with a mean operation temperature. The day 4 is a day with a high operation temperature and clear sky. And the last day is a day 5, is a day with the operation temperature below ambient temperature and a clear sky. So this is the conditions for the quasi-dynamic test. In order to evaluate the performance, there are some key performance indicators. So these performance indicators are related in the are in the standards. So the first one is the measured coefficients for the calculation of thermal output. So the parameters that I have showed before in the equation. So the A parameters that will be evaluated. The another one is the incidence and angle modifier of the collector. So the performance of the collector for different incidence and modifier. The power output per collector unity. And the last one is the collector annual output for several temperatures. This is according to the one annex of the solar key marker certificate, which is the Senocalc annex. So this is more or less my presentation regarding the thermal performance.
Perfect. Thank you very much, George, for the presentation regarding the experimentation and experimental setups that are needed for the performance characterization of PVT collectors, and also to put into the framework of the PVT for You project that we're working on. Now I will give the floor to your colleague, to Carlos, to also enlighten us a bit regarding the electrical characterization as well and performance testing of PVT collectors.
Now I will present the guidelines and experimental setup for PV at performance testing of PVT collectors. As George says, we don't have a specific international standard for testing PVT collectors. So solar key mark certification of PVT collectors is only possible by applying specific rules for PVT. According to this standard, the thermal performance of PVT must be tested with synchronous thermal on the electrical conversion of solar energy under maximum power point conditions for PV. In order to carry out the experimental tests in LNEG, we have made some modifications to the existing electrical test bench in order to allow testing the PVT or a CPVT collector at maximum power point of the PV. To determine the electrical performance of the PVT and or CPVT collectors also at different test conditions that you have. The collected data will be used to generate a regression curve that is used to correlate the electrical efficiency with the average temperature of the fluid and the ambient temperature and the irradiance. In terms of the electrical performance of the prototypes to be tested, we have a concentrated PVT prototype and under development of the PVT for a project, and the PV cells on the top and bottom of the PVT receiver are subject to different temperature and irradiance conditions. And so we must be connected to independent inverters with maximum power point tracking capacities in order to ensure their operation at the maximum power point. On the left, we can see the connected top cells are connected to one inverter, and the bottom cells are connected to other inverters. The quantities to be measured are the DC voltage on top and bottom, the DC currents on top and bottom, the cell's temperature, the solar irradiance on the plane of the collector, the quantities to be calculated, the DC power on top and bottom, and the conversion efficiency of the PVT collector in the electrical convection. The text bench installed at LNEG. We have these equipments, a multimeter data acquisition system, Kisley, model 2700, with a switching model 2700. The voltage range for measurement of the DC voltage are the 100 volts, and for measuring the DC current we use shunts with a conversion current 40 amperes to 75 millivolts, and use a multimeter in the range of 100 millivolt. The installed inverters are Enphase IQ7A microinverter with these parameters of operating. We have also installed a new electric panel with connectors for the PV, where we installed the shunts, the inverter modem, and also some AC grid protection devices needed. The total DC output power of the PVT under test can be calculated from the sum of the DC output power on the top and bottom cells. So with this expression. The power, for example, the power for the cells on top can be calculated by multiplying the voltage with the current. We have also the PV conversion efficiency for the PVT, the electrical efficiency can be calculated from the total power done by the sum of the power on top and bottom over the incident solar power is obtained by the irradiance to multiplied by the area of the PVT. On the other hand, we can measure also the PV characteristic curves of the PV devices. As you know, PV models and other devices in the market must report the electrical parameters obtained under standard test conditions. The temperature of the cells at 25 degrees and the solar irradiance with 1000 watts per square meter. LNEG, we can obtain these curves and you can trace it separately for the cells on top and bottom. On the left, we can see an example of expected IV curves for the PVT cells. In order to obtain the parameters at STC conditions, we need to use as guidelines some ESC standards. So we can use this standard is related with the measurement of the photovoltaic current voltage characteristics, so the determination of the IV curve, and the other in order to calculate the IV curve at STC conditions. So the procedures for temperature and irradiance corrections to measure IV characteristics. At LNEG, we use this equipment, a curve tracer PVPM 1040C, produced by PV Engineering, and we have also temperature sensors and irradiance sensors, pyranometers, and PV reference cells. This curve tracer has a very large range of measuring voltage from 25 volts to 1000 volts. You can use it with a single module or for a string of modules, and for currents from 2 amperes to 40 amperes. The range of temperatures of the equipment is -40 to plus 120 degrees. The irradiance is until 1300 watts per square meter. So in general, the electrical power of the P devices can be determined from the IV curves, measured on the different test conditions, and you can use this standard as guideline. So we have an example of the IV curves you can obtain for PVT cells, a PVT with the cells on top and bottom, we can obtain this type of IV curves. So in green we have the point, the maximum power point of the curve, and you have the parameters you can obtain for the two situations. So we can obtain the short circuit current. For example, for this, the open circuit voltage, the maximum power point, the fill factor is calculated from the other values. The voltage at maximum power point is this. The current at maximum power point obtained in this point. And the power conversion efficiency is done by the maximum power divided by the incident solar energy. So the second generation of prototypes of the PVT collectors will be tested from the beginning of 2026 at LMEG. This will be done in Lisbon, Portugal. We can see in this picture an example of concentrated PVT in testing at LMEG in the past. And for my side, I have no more slides. I know. Yes. So thank you.
Thanks, Carlos, for the nice presentation regarding how to characterize the electrical performance on PVT collectors. And actually, I was going to ask you, like, regarding the IV curves that you presented in one of your last slides, like, from where did you take them from? And I think that those were measured with the previous Solaris collector that you had it installed in your facility before. So I'm actually really excited to see this, and I think that everyone that has had the opportunity to characterize electrically PVT collectors is not quite as straightforward. You have to face different challenges because you're using off-the-shelf devices for data acquisition and measurement that comes of course from PV, and sometimes, especially when you're using customized PV cells arrays, could be rather challenging depending on the voltage levels and currents that you're managing in your configuration, right? So having clearness about how to do it, I think that will also help other, like, early stage researchers in the area to have a better idea on how to do it. So thank you very much, Carlos, again for your presentation on this topic. And now I will actually give the floor to Mark Daneman, which is also a senior researcher at DTU, as well as FAN, that we had it in the previous section. And he has actually a very nice topic regarding testing PVT in extreme conditions. And I think that he's going to be using some of the nice pictures that he have taken in the last years. And so, Mark, the floor is yours.
Yes, thank you. Can you hear me and see my screen?
Perfectly.
Yeah, great. Yeah, thanks for the opportunity to present this. And the title, Testing in Extreme Condition, that was actually something maybe you came up with, even, or something, at least your team. But I just said, okay, let's just go with that. It might not be super extreme condition, but at least it's focusing on testing during winter time. So, and and I will, even though we're also part of the PVT for EU project, I will now present some results from a previous project, a project called ITB, which was funded through the Danish Energy Agency. And we, DTU, in a collaboration with an architect, GXN, and then the company Racel, which is a Danish company who is developing PVT collectors. And in this project, the idea was to try and develop PVT panels which could be sort of fully integrated into a roof and potentially sort of replace the sort of or the normal roof elements. And so that's a starting point. And Here's some pictures of our PVT collector test facility, and why it's specific for PVT. It's because it's we can control the forward temperature to this to the collectors down to around -10 degrees, which is relevant when you use the collectors as a source for the heat pump. So this is in our frame the systems we look at is PVT heat pump systems where the collectors are directly used as source for the heat pump. And we have a experimental setup where we have the collectors, and on top of it we have our DTU climate station where we collect all our weather data, and we can have a lab view interface and control pumps and stuff, so we can actually run our or let run our sequence run for days or weeks or months with and control to have stable inlet temperature and stable flow. And one of the things we considered in this project was about how these panels are integrated into the roof, or how the way they are mounted actually affects the roof temperature or the roof condition. We have in some previous projects seen that there was problems with condensation and mold forming in the roof when you had PVT panels mounted in a not good way, sort of, can you see? So therefore we considered, depending on how the panels are mounted, in the top right we have the panels mounted sort of free, a little bit, hovering above the roof, and wind can easily pass below, or natural convection can also easily pass around it. But this might not be how the panels are mounted in an actual system, especially not if you talk to an architect. They would love to have a nice looking roof where uniform, so they would mount a lot of panels side by side, maybe with a small gap between them, or maybe even totally closed, so it's like the roof is one uniform structure. And we were curious first about what would happen here below the panels in these conditions, or so we did some different tests to compare. So we've ran with an inlet temperature of -3 degrees, and by the way, you can see on there's of course this causes condensation and then later on ice formation, which you can see on some of these pictures. And if we run with inlet temperature of -3 and ambient temperature is 6 to 10 degrees, what is the roof temperature below the panels? So in the top right, we see that the temperature of the roof surface, sort of the temperature of the roof surface, the temperature measured at the roof surface is roughly the same as the ambient air temperature. Makes sense. You can have lots of convection, air flowing around, but as soon as you start to narrow this, in the bottom left, for example, if you have lots of panels side by side with a gap around them, then the temperature on the roof surface drops. So in this case, it's 2 and 4 degrees lower than the ambient air temperature. And to the right Here there is sort of no gap, completely closed, and whoops. Yeah, you can see the temperature below these panels is significantly below the air temperature. And yeah, these two panels we tested here, one was the similar PV and absorber. One has 2 centimeters of insulation on the back, and the other one has the absorber exposed to the air. So yeah, this is one thing we looked at, and another thing is that we considered is what is the actual performance of these panels, or if you characterize them according to standard, like George explained earlier, do a quasi-dynamic test analysis, and you get some coefficients. I think this is relevant due to the coefficients you get from a manufacturer, or the coefficients you get from testing your panels. It might be to have some values, but if you install the panels on a roof next to each other or in another way, then they might perform a little bit different. So here are the values we got from with and without these frames around it, and for the insulated and non-insulated. And if you have experience with doing this QDT test, then you know a little change in the conditions will cause one value to go up and another value to go down. So it's a little hard to evaluate. But if you look at, for example, these two values, which I've circled, is the heat loss coefficient and the wind-dependent heat loss coefficient for this uninsulated panel, first tested without the frames. Fairly high wind-dependent heat loss coefficient, but then if it's mounted with the frames around it, sort of as is many panels side by side, then A1 coefficient goes up, and the wind dependent goes a lot down. So, and again, these values, what can we use them for? If you have to see them in a simulation system, maybe a yearly simulation, to really know what is the effect on a full system. But if you try to run this simulation, or you sort of derive coefficients in a more simplified way. So if you just have an optical efficiency and one heat loss coefficient for these panels, is sort of in a super simplified way, then you can maybe more compare directly to see what is the effect of mounting the panels super free or close to each other, sort of like this. And there you can see the A1 coefficients is reduced by, what is this, a little less than 10% if you mount with the frames. Yeah. And here's the collector efficiency expression from the ISO standard, which Shorks also presented, and below is this extended collector efficiency expression, which was, I think it was originally presented in this paper by Bunea and Perez in 2015, which should also take in condensation, rain, and radiation from the backside of the panel. What it does not really include also is this ice formation and snow. So ice is formed, of course, when you have a very low inlet temperature. Could easily happen for a heat pump system, wintertime, and first condensation, and later on this ice formation. So we tried to derive these coefficients from our measurements, but it at least from our experience, turned out that it was not possible to sort of derive all the coefficient in this this extended expression in one go. They turned out insignificant, or they turned out really weird. So at least so far we did not succeed. But again, we're interesting to try and look at what is the effect of rain on a PVT panel. So it could or will happen that a lot of rain, winter, Denmark, Northern Europe, PVT panel is running. So again, if you try and look at it in a simplified way, if you look at periods, or what coefficients would you get if you only have the simplified optical efficiency and one heat loss coefficient for this, the insulated and the non-insulated. If you look at only periods without rain, you get a A1, say 9.5. If you look at it for only rainy periods and do the same analysis, you will get a heat loss coefficient of 17. So of course the rain has a very big impact on it. And similar with condensation, we were not able to get meaningful values from the full expression, but we could get some if we just look at a A1 coefficient and the A10, which is the condensation. So here we take measurements where we only look at periods during the night to avoid the effect of the solar radiation. And so how can you quantify the effect of the condensation? So if we divide our measurements up in the first line is all our measurements, and then here the second one is where we have a relatively high inlet temperature, so above 10 degrees, we assume no or little condensation. The next line, we would have inlet temperatures between 0 and 5 degrees, so we would assume definitely condensation. And then the last one is inlet temperatures below 0, where we would assume condensation and ice formation. So you can see definitely the A1 coefficient will increase. There's for sure an effect. And if we try and run the QDT with both A1 and A10, then we also get some an A10 coefficient, which is there. And then as soon as we go from condensation to also ice formation, then it has a very large impact. Yeah, hope it makes sense. And now I'm wondering if this will show. We have a video to show. So this is from testing during winter. We have a snowfall on the collectors. Snow stays on some of the panels and not all of them. And here where the snow falls down, it's the PV panels which are not cooled, and the panels here where the snow remains, that's PVT collectors where the inlet temperature is below 0. So here we can see that for a couple of days snow remains on this collector, and of course it doesn't produce electricity. And what happens to the thermal power? Here's just some measurements from November. The top graph shows it's just the snowfall. So we can see in around 21st of November, we get 3 days with snow. And below is the measured electricity output from 2 panels. One panel is a PVT panel, but it's sort of passive, so no circulation of fluid, and the other one is active, so we have cold fluid running through it. And we can see from the first days that when we cool the panel, we increase the electricity output a little bit, but in the days where we have the snowfall, or from the 21st, we see that the panels which are cooled, they produce a lot less electricity because snow remains on the panels. And yeah. The last few slides is some measurements where we're trying to show also in a simplified way what happens when snow or this ice formation is formed. So the top diagram is the red curve with the thermal output, and the blue is the radiation, and the gray marked area, that's the nighttime. So if you focus on the nighttime, we have a heat transfer fluid, or cold heat transfer fluid coming in, and ambient air temperature is higher, so we get a power output of here in this case 200 watt. Below is the top green is the air temperature, ambient air, and the red is below is the different in and outlet temperatures, and then we calculate a simplified heat loss coefficient there. So we compare this first scenario is where we have no ice or no snow on the collectors. Then we have a situation where we have this ice formation from the condensation. It's both on the front side and the back side. And in this case, we can see that if you just pay attention to the heat loss coefficient, that it sort of decreases during the night, which should indicate that we get more and more ice on the collectors, and heat transfer or the heat loss coefficient is reduced. It can still extract energy, which is good. But what happens when there is snow on it? That's what we can see here, that the thermal power drops to 0, and also this heat loss coefficient is close to 0. And yeah, we have had from our partners, Racel, they told us, or they also have experienced this problem in real life, that they have what to do with the systems when there was snow on them. And yeah, I think time is running out as far as I get. And last I want to say is that we have a new research project. It's a local funded project which is just starting up now, and in this project we will have to, or will look into more of these kind of things for the panels, winter conditions, condensation, ice formation, snow, and all this, what we can experience, at least in the north, when we have a PVT panel as a source for a heat pump. And yeah, so if anybody is have experience, want to share something about this kind of things, you're very welcome to get in touch. Yeah, that was it. Thanks.
Thank you very much, Mark, for the insightful presentation, especially for the ones that haven't had like experience on doing this kind of experimentation in what we call, as you mentioned, extreme weather conditions, at least in the low temperature part, I guess. So now we can actually move forward with the last presentation of the section, which is basically something that is quite new. That is maybe a tentative collaboration that we will have with EU Solaris. In this case, I'm not sure if it's going to be you, Joao, that is going to be presenting the initiative. Yes, I can
Yes.
see that you're
Yes.
ready to do it. You can move forward. Thanks, Joel.
Okay, thank you. So good afternoon to you all. So unfortunately, the EU Solaris ERIC General Manager Diego Martinez couldn't attend today's workshop, but he asked me to present on his behalf. So my name is João Cardoso. As you probably know, if you saw my presentation in the morning, I am from the Portuguese National Laboratory of Energy and Geology, but I'm also a member of the EU Solaris ERIC General Assembly meeting. And with this presentation, I'm going to try to convey to you what is EU Solaris ERIC and the activities that we carry on in this research infrastructure. So EU Solaris ERIC is the European research infrastructure for concentrated solar power. This is the official name of this infrastructure. Actually, nowadays it's more about not only concentrated solar power, but also concentrated solar thermal, so encompassing also heating applications. So, sorry, the presentation is not moving. Okay. So EU Solaris is integrated within the European Strategy Report on Research Infrastructures that is made by ESFRI. What is ESFRI? ESFRI is a strategic forum formed by the European Union member states and the European Commission in 2022 to coordinate a common strategy on research infrastructures. So the objective of ESFRI is to develop a pan-European research infrastructure roadmap to support the scientific integration in Europe and strengthen European research infrastructure's visibility and international impact. So ESFRI includes scientific infrastructures, both centralized or distributed along the different nodes, which corresponds to a given defined strategic area and are considered to have a unique nature and are identified by the European scientific community as adequate for carrying out high-level research in their field. So in this case, ESFRI regularly surveys the research infrastructure landscape and creates these roadmap reports. The next report will be created in 2026, so next year, and it divides the European research infrastructures in two levels. One are ESFRI projects that are research infrastructures that are still in their preparation phase, but that have already been selected due to the excellence of their scientific profile, and ESFRI landmarks that are research infrastructure initiatives that have already been implemented and are operating, which is the case of EU Solaris ERIC. So just to give you a brief overview, in the 2024 portfolio, there are 22 projects, only 2 of them in the energy sector, which is the one related with the materials for fusion and another one related with renewable energy marine research. And there are 41 established research infrastructures. They are called the landmarks, as I was saying. And we have 3 within the field of energy. Excel, that deals with carbon dioxide capture and storage. EU Solaris ERIC, that I'm going to present you now. And one related with also materials and nuclear energy, that is the Joule-Horowitz reactor. So what is EU Solaris is an ERIC, which is what is an ERIC? It's an European Research Infrastructure Consortium. So it's a legal entity that has been set up by the European Commission through an implementing decision after being proposed by the European Union member states, or by a set of European Union member states. To be an ERIC, you must be an European joint venture. You must provide effective access to the European research community. You should contribute to the mobility of knowledge and researchers, and you should contribute to the dissemination and optimization of the results. So the creation process of EU Solaris is actually a long one. It started in 2010 with the design phase, where we applied to be included in the S3 roadmap as a project for the first time. Then there was a follow-up project funded by the European Commission that enabled us to complete the preparatory phase through 2012 and 2016. This was the EU Solaris project. And after the end of this project, there was a period for the implementation phase, the development of statutes and other documentation between 2016 and 2022. And finally, by the end of 2022, the European Commission recognized the EU Solaris as an ERIC in October 2022, and we were formally established on January 2023 with our constitutive meeting that was carried out in CIEMAT in Madrid. So currently EU Solaris has 4 members. Remember, the members are the states. They are Spain, which is the statutory seat of the infrastructure, France, Germany, and Cyprus. And we have 2 observers, Portugal and Greece. Actually, Portugal has now applied to join as a member, so we are expecting to be upgraded to the member state by the end of this year. So what is not EU Solaris ERIC? EU Solaris ERIC is not a project. We are not a company, and we are not a network. We are a long-lasting consortium of countries that are focused on the joint development of our research infrastructures around a specific topic. In this case, concentrating solar thermal, and we have been established under an ERIC. What we do and what we would like to do, because we are still at the beginning, so some of our activities are just starting. We participate on calls, funding calls, focusing on research infrastructures. We participate on networking activities, for example, cost actions and others. We can represent by invitation the CST community. This has happened in some calls, for example, within the WIDERA and the European Innovation Ecosystems programs. And we have funds to develop our own project within the consortium, which we call internal projects. What we don't do, we don't participate in conventional R&D funding calls, so that we do not compete with our own partners at the ERIC. Okay. So how are we funded? Every member country contributes with an annual fee. It's actually not so expensive. It's 20,000 euros per year. And we get funds by participating in externally funded projects. And actually, we have been very successful on these. We have, for example, in 2023, we applied ourselves in 5 proposals and we got 4 of them. And also through in-kind contributions from our member states. So besides, we also have other countries besides the 6 ones that I previously mentioned that are also in the process of being involved in this initiative, which in this case are Italy and Turkey. So which entities can be a member of the ERIC? Member states, associated countries, third countries, and intergovernmental organizations. And these member states can be represented by public entities to exercise the rights and the obligations on behalf of the countries. So we have given governance structure. I'm not going to dwell too much on this. You will have access to the slides and you can see them. So we have a General Assembly as the main decision-making body. We have a central hub that coordinates the daily operation of the ERIC, and perhaps more interesting is that we are a distributed facility, so we have nodes in the different countries. So, and a given node of a country can be composed by 1 or more entities from these countries. Now, perhaps more interesting, what are our lines of action? So one of the lines of action is the provision of access to our research infrastructures. So we want to improve the accessibility and interoperability of our research infrastructures so that we can provide better services to the research community and to the industry. EU Solaris offers a single user entry point, or aims to offer a single user entry point where the facilities, the resources, and the research services can be effectively offered to users of these services. And perhaps interestingly, we will have a pilot access campaign foreseen for 2025. So we expect to launch it before the end of this year. Another line of action is the coordination of our members' research infrastructures. Also, the collaboration with industry, reinforcing our network with industry, providing adequate testing services, unifying and defining new test protocols and standards to provide the best possible test facility and experts to the industrial community and also to the research community, of course. Another major line of action is dissemination. So we offer training services for industry, and we have also established training networks to grow the next generation of CST researchers. So for example, we have established an annual doctoral colloquium and a summer school. So you can see here the one that we carried out last year in France. We also aim to lead and coordinate the dissemination of results and good practices. So, for example, we established prizes for best doctoral thesis on CST-related topics, and also a prize for outstanding contributions to the improvement of the research infrastructure's capabilities and services. Also, we have internal projects. We have currently two internal projects ongoing. One started on 2023, dealing with new techniques to assess soiling in solar technologies in a more automatized, faster, and capable way. And also in 2024, a new project started related with the optical analysis of heliostat fields. You can see these further on by following this link when you have these slides, the presentation. And also we are participating currently in several projects, namely projects related with the strengthening of the bilateral cooperation on research infrastructures with Latin America. So as is the case of the EULAC Energy Trend, we are coordinating mobilities for Ibero-American researchers to European laboratories. Not only in the field, in this case, it's not only in the fields of CST, so it's a more broader project. Also the Cactus, which is dealing with enhanced solar PV performance through improved research infrastructure for adapted climate conditions. And here we are leading a work package dealing with the enhancement of research infrastructures. And we are also coordinating the provision of access to 7 research infrastructures on CST through the Rise Energy project, where EU Solaris is also a partner. So we also have our own EU-funded project that is Solarize, that aims to support the development and the further development of EU Solaris. I'm not going to delve too much on these. You will have more information on the slides about these, but maybe I will just highlight that we aim with this project to strengthen EU Solaris ERIC at internal level. We also are dealing with the positioning of EU Solaris ERIC at external level. That's why I'm also talking to you, because there are areas that can be applied to PVT systems. For example, concentrating PVT systems, the characterization of concentrators, the development of and analysis of the concentrators, but also with other PVT collectors, for example, in terms of material analysis, material evaluation, durability, and these type of things. And the final goal, which is to provide enhanced services to the European research communities. So I conclude by leaving some key messages for you to take away. So EU Solaris is not a project, it's neither a network, it's a long-lasting consortium of countries under a specific European legislation. The members are the country states with leading research infrastructure institutes from those countries. This is all about research infrastructures focused on internal coordination, delivery of services, capacity building, development of testing procedures and tools, policy making, and so on. And we are very open to collaborate with the PVT community and to find ways of also develop research with you in our infrastructure and try to develop further the solar sector. So this is a very brief presentation of EU Solaris. There is much more to come. I'll be available for questions. Thank you.
Thank you very much, Joao, for the presentation regarding EU Solaris EDICT. So I think that we're actually ready to restart with the workshop. We still have 2 last presentations. So bear with us. I think that is going to be has been a long day, but also quite interesting. And hopefully the next 2 presentations are going to be still interesting for you. I think that I strategically placed mine presentation at the end, so I can use some of the background that many of you have already presented. So hopefully it is going to be a bit more easier for you to understand what I'm trying to convene today. And my presentation is going to be about PVT technologies, future trends and challenges. And I think that, as I mentioned before, many of the information that you have already seen throughout the day is going to be useful for you to understand what I'm going to be sharing with you now. So this is a brief agenda of today. Actually, let me, because nobody's going to be keeping my time, I guess, right? So I will do it myself.
Yeah.
So then this is the agenda that I have for today. I'm going to be first introducing what I call the current status of PVT using a methodology that I found quite interesting, which is called the hype cycle. And then we will go for, I will be reviewing some of the collector level trends in research and development. After that, I will be reviewing something about system level and deployment of PVTs. And last but not least, I will also be sharing with you some of what I think, at least in my perspective, are the challenges that we are facing currently and we're going to be facing in the near and medium term for PVT deployment. So, as I mentioned before, when I was preparing this presentation, I was thinking to myself, like, how should I present the current status of PVT? We have so many reports that haven't already addressing this topic in solar thermal, in solar heat worldwide report, for example, where we are like looking how the different PVT manufacturers have been increasing in numbers, and also not also in number of manufacturers, but also in installations. So I thought, like, bringing a new topic that I've never seen before, at least in PVTs. I know that many of you have already reviewed about what is the Gardner half cycle, and I decided to use it as a methodology that hopefully is going to be quite representative for what I'm trying to define as the current status of PVT. And for those who doesn't know about the Gardner half cycle, I remember learning about this methodology when I was doing my master's, actually. And it is a graphical representation of the maturity, not only in technology level, but also in the adoption and a social application of a specific technologies. And it explains the current status of the technology and the current road or pathways that the technology needs to undertake from the very beginning to when they have already reached the market maturity. Something important to mention is that actually Gardner usually develop these hype cycles yearly, but for a bit more wider approach. For example, solar photovoltaics, or for example, green technologies, or automotive solutions for the future, or something like that. So, where they categorize the different types of technology in a more broader aspect. Nevertheless, I decided to use it just for us to have a clear overview of how PVT is also evolving in time. As I mentioned, it is important. The Gardner methodology also divides categorize this development in different stages that we will see now. But something important to mention is that the cycle isn't isn't a strategy to compare good versus bad. It's just about timing and evidence, like what it is out there regarding patents, what is out there regarding proven demo sites, proven laboratories, proven systems that are working out there in the market. So I thought that it was a very good methodology that I can use in order to try at least to assess the current status of PVT. I'm going to be reviewing, just for you to understand better, before jumping into the hype cycle of PVTs, what are the different stages. We have 5 different stages in the hype cycle. The first one is the innovation trigger. When we have a new idea, a new prototype, a laboratory test, the pilots and demos that are happening. Then we have what is called the peak of inflated expectations, when attention explodes. There are optimistic, or at least what it seems to be optimistic returns on investments, and also fear to be kicked out of the investment. So usually this is the state where investments or early stage adopters try to invest in a certain technology just because they are being afraid to be left over, right, or left behind. Sorry. Then we have the trough of dissolution, when reality bites, failures, delays, and also some vendors exits, which I think that some of the people that is here has some experience and has some knowledge about, at least on PVT. But this is something that we need to pass through. Then the technology matures. We have credible cases, case studies, second-generation products appear, which are basically the results of making new developments for those manufacturers or both developers that stayed in the market and try to enhance the technology and to approach the failures that they had before. And last but not least, we have a proven niche and repeatable value. A predictable performance and returns of investment. So basically here is where the technologies are already well placed in the market, and the investors and the people that is going to be buying those products already know and they can trust about the profitability, at least of those technology. So this is the hype cycle, the Gartner hype cycle that I decided to use in order to define, or at least try my best to define the current status of PVT. And something that I had to mention is that it is a work that is going on. So I'm going to be developing this in the next months as well. And of course, any feedback is well received. So this is what I call the simplified hype cycle for PVTs. It's an own elaboration and is in progress, of course. And I will start from the plateau of productivity towards and then to the right until I reach the innovation trigger. So we can see that in the plateau of productivity, we have uncovered PVTs with heat pumps, and also like a bit behind, we have air PVTs, covered PVTs, insulated PVTs, and evacuated PVTs that are in the slope of enlightenment. And they are like really close to plateau of productivity. Something particularly here that I was struggling a bit to place was air PVTs, because air PVTs are already in the market, as you see in the reports of Solar Heat Worldwide. They were actually quite a very important bunch of the installed PVT capacity, and still are. Nevertheless, you know that many players and many manufacturers have stopped doing air PVTs and deploying these kind of solutions. But I actually found a really good information that Raquel showed us regarding that there is a slight recover on air PVTs. Hopefully, we will see that happening soon. Then we also have PVT with district heating networks. As you might already know, we have different companies that are looking into that configuration. I think that the one that I can discuss is the one that Agora has in Cuenca in Spain, when they are like having integrated PVTs with district heating networks, especially in low temperature district heating. We're thinking about 4th generation and 5th generation district heating networks, where basically you're trying to reduce as much as possible the operating temperature of PVTs, because and therefore you will increase also the performance of and the yield that you will have from such systems. Then we also have PVTs with PET, thermal energy storage. We have some demos, some pilots, and even some commercial plants in Denmark specifically, also in some Nordic countries, like in the Netherlands and in Sweden as well. And in the bottom of the trough of the solution, we have maybe some solutions where they're using advanced absorbers and advanced hydraulics. and also CPVT. We know that there are some manufacturers and some systems that have been installed in the world, especially in South Africa. We have some options also in Europe. And I particularly was very keen to visit, like a couple of months ago, one of the first CPVT systems that has been working. I'm not sure if it's worldwide, but maybe Joao can tell me. Do you remember how old was the CPVT system that we visited in Stockholm? Was it?
That is very old.
Was it like 50
years?
20 years, right?
I think it was installed 2002, something like this.
Exactly. And do you remember who was the deployer?
Vattenfall.
Vattenfall, yeah.
It was Vattenfall that designed it. It was Björn that designed it.
Björn, yeah, especially with the concentrator.
Concentrator, right?
Exactly. So sadly, of course, after 20 years, you might as well, of the ones that know about PVTs as well, knows that maybe the electrical parts is not working just as we were expecting as well.
It was hand soldered at the time.
Exactly. It was
the big.
Exactly. It was a early technology, let's say, but it was really interesting to see that at least the thermal part is still fairly working. So yeah, I think that CPVTs are in that part, and there are some manufacturers that are trying to put into the market again CPVTs, especially given the additional increased temperatures that you might have that will open the floor for industrial applications as well. Then in big of embedded expectations, we have, for example, PVTs based on perovskite and silicon tandems. We saw that happening in Intersolar 2024, where it was Sunmax, yes, and Oxford PV presented the very first perovskite silicon tandem PVT collector. And they were planning to, or at least it was in June last year, they were planning to put it in the market in the next 16 to 18 months, if I'm not mistaken. I don't have details about what's happening in that regard, but at least they introduced it in a commercial setup, such as Intersolar. Then we also have PVTs with the spectral splitting. We have some companies that are developing some prototypes there that are reaching TRL4, TRL5, or even higher. And so that's why they are in peak of inflated expectation, because of the additional value of having this decoupling, the thermal decoupling of the PV part with the thermal part, which is something interesting. Then we also have some vacuum flat PVTs. We have some projects going on in Germany actually regarding that. And in early stage of development, we also have something that I found particularly really interesting regarding dual purpose PVT. Which are like they have like dynamic losses. We were discussing in some presentation regarding the importance of the different thermal coefficients, right? But we know that whenever we have a PVT panel manufacturer, then those thermal coefficients are going to be static, of course, depending on the situations. And these ones are concepts where you actually can tune. Depending on the need, these coefficients. So I found that rather interesting. Something is happening in Turkey in that regard as well, and also in the Netherlands. Then we have high vacuum flat PVTs, also in early stages, and CPVTs with the spectral splitting, which also folks of Imperial College are working on. We have some projects in Horizon Europe, a Horizon Europe project that is working in that regard. That is, of course, in early stages and lower theory levels. So something that I have to mention here is that you know that this kind of assessment is as representative as the data that you have in order for you to develop. So as I mentioned, this is a work that is under development. So I will be really happy to collaborate with some people that has a better understanding about this, such as Verbalep, right? But yeah, I wanted to introduce this methodology, and something that and the takeaway here is that most of the PVT applications are like going through the slope of enlightenment and trying to reach the plateau of productivity. So the technology is sound. There are some proven cases, but there are still some limitations that are happening. We are still in a growth stage in the hype cycle. Nevertheless, challenges in operation and maintenance, complexity, and lack of awareness hinders its progress towards the plateau of productivity. We need to watch out, especially for the technologies that are in early stages, to make sure that the durability at higher temperatures is ensured. Also, something about the standardized KPIs and data whenever we are assessing the results and the yield of such systems, and this is for one of the focus of task 73. and also to make sure that the workforce and commissioning complexity is not so relevant, and because it can limit the scale, even if the technology has been proven to be good. Regarding PVT collector R&D trends, I'm going to be brief in this case because I'm sure that many of you already know about this. I will divide this in thermal absorbers and in PV modules. In thermal absorbers, we have different research going on and developments in commercial level using aluminum roll bond and direct flow. When you are trying to lower thermal resistance and of course to scale the production of thermal absorbers so you can reduce the cost. We also have a research regarding different heat transfer geometries to enhance the heat transfer, of course, like fins, wavy plates, shading pigment, and bionic design, such as the one that we can see on the right. In the material choices, also some of the presentations were discussing about this. We have regarding the uncovered and covered collectors, depending what you need. New configurations like bifacial, especially for air PVTs. And when you want to play with heat loss reduction or increase, depending on what you're planning, when is your application, and you're going to be playing basically with the thermal efficiency curves that we can see here, and that was also introduced in one of the presentations. Regarding PV modules, you know that historically PVT have been using off-the-shelf PV technologies just because of cost constraints. Some of the manufacturers have tried to develop their own, but with a cost, of course. Nevertheless, there are some alternatives. For example, single solar cells to increase the active area of the photovoltaic area, and also tandem configurations with perovskite and silicon, such as the one that I mentioned before, and that has been developed with Sunmax and Oxford. They call it solar hammer, by the way. And also one of the approaches is to lower the temperature coefficient of the PV stacks, also looking to encapsulants, anti-reflecting textures, and also other coatings that are also targeting to selectively direct the different wavelengths that you have in the impinging in the PVT collector. Regarding system level deployment and trends, as I mentioned before, we have PVT with heat pumps that was already well introduced and studied by your folks at KTH, having PVT used as evaporator as a source of preheats to increase the seasonal cup. We have some very proven technologies in commercial projects on that by Triple Solar, Dual Sun, just to mention a few. We have also, of course, the basic PVT and for domestic hot water tanks that were also briefly introduced by Raquel of NDEF. PVT with pit thermal storage and heat pump integration when you have summer charging of the thermal storage by the PVTs, and then you need a winter lift by a heat pump to supply to the district heating networks depending on the temperature that you're targeting. And last but not least, also PVT with district heating networks to feed return lines or to lift also, or to have heat pumps lift stations such as the collectors or the project in Cuenca. For system level deployment and trends, we have hydraulic simplification when we have prefabricated skids, quick connection manifolds, and low pressure dropped layouts, plug and play configurations. We are targeting a standard KPIs, as I mentioned before. Something that is quite important is installers training, because we need also hybrid electrohydronic skills from people that is going to be installing these kind of systems, and we can do that through reaching installers associations, manufacturer academies, such as I know that Dual Sun has a very good one, and also developing installation checklists. Also, something that was mentioned before, we need data openness. We need to push to open data sets for the manufacturers and the people that has been commissioned these kind of systems, so we can study and we can do some of the research and to promote replicability also of these kind of systems. Regarding the challenges, we have durability of hybrid stacks, electrical thermal co-optimization, of course, new PV technologies, as I mentioned before, flow distribution and decrease of the pumping power that has to be considered also when you're estimating the yield of a PVT system. Standard testing, specifically for air PVT collectors, or to harmonize how we are going to be testing such collectors, and validated models as well are quite important. Regarding deployment challenges, as I mentioned before,
installer skills gaps, design and commissioning complexity that could be really hindering the deployment of the technologies, bankability and finance. We have limited method case libraries. That's what I mentioned, that it's important to push for openness of data sets. Policy and incentives, we discussed a bit about PV only or solar thermal only schemes, even though sometimes that could be open the door for PVT as well. Sometimes it could be beneficial as well. Grid and permitting, that's something that we can inherit from PV, I guess, in some countries, and lack of connection between stakeholders. And this is something that I would like to emphasize here, because I see that PVT has been really fragmented in terms of research and development, in terms of deployment and also training, and that's the very reason why we are here as well. And I think that is also sets the grounds for the next presentation and the initiative that we're having within the PVT4EU project, that is called PVT Nexus. And I will leave the floor to Mariam and to Tinta to explain us a bit more about that. So that's all from my side. Thank you very much. I hope that you find the presentation interesting, and you can contact me if you want this information. Thank you very much.
Perfect. I can share them?
Yes.
Now the best presentation.
Exactly.
Yes. Okay, thank you so much, Ivan. And I think considering the number of people rejoining online, I can say that maybe there is some quite interest in the PVT Nexus we are launching here today. So first of all, my name is Mariam Shalabi. I will be presenting PVT Nexus today with my colleague Gintari from MG Sustainable. And I think following what all the presentations said today, and even specifically mentioned by a couple of presenters, the need for awareness raising and more communication between the PVT community at large, this is a very interesting initiative, and it comes at a point where it will be very useful and very needed. So starting, what is PVT Nexus, and to explain what we will be launching today, what we are presenting today. So I think everyone already knows quite a lot about PVTs and what their potential is, but however, despite their very large potential, there is still, they are underutilized globally, we can say. And because of that, we have launched the PVT Nexus as an initiative within the PVT4EU project. PVT Nexus is meant to be a research network for PVT technologies and systems. Within that, we are targeting two groups. Let's say first are early stage researchers, which are the students, and secondly, the mentors. For these two target groups, we have 5 different structure elements, or let's say benefits, that they can gain and interact with within PVT Nexus. Firstly, I will be introducing the structure I just mentioned, and then Gintari will be going over the two target groups' profiles and how you can be part of PVT Nexus. So starting, we have internships and projects as 2 parts of PVT Nexus. First, of course, there's always a continuously present gap between academia and practice, between the workforce and the researchers and the students. And within these internships, we are aiming to explore all the opportunities possible for internship and work offers and opportunities within the PVT Nexus network. Secondly, for projects, we aim to encourage all the PVT Nexus members to work together to join and collaborate on ongoing projects, as well as work together on joint proposals to apply for funding from different EU programs. I'm sure everyone here is familiar with so many programs already. Then we also have career opportunities as another big element that we are targeting with PVT Nexus, with the aim to expand all the members' professional profiles within international scientific networks, and to also allow them to showcase their work within the international PVT community. Fourth, we have infrastructure. And with this, we aim to explore different infrastructure offered by the PVT Nexus network, offering access to their laboratories, to their testing facilities, or even to their technical equipment in order to foster collaboration between the different members, and to also foster innovation and to reduce double work, reduce the need for equipment that can limit research or can limit expansion of new innovation just for the lack of available infrastructure and available equipment. So all of these four elements I just mentioned, whether they are the internship, the projects, the career opportunities, and the infrastructure, will be combined together in the big initiative we are having within PVT Nexus, which is the matchmaking platform. So this is as a broader initiative within PVT Nexus that is aimed to be a collaborative working platform. This is envisioned to become a central hub where early stage researchers, mentors, and stakeholders can connect together. They can exchange knowledge. They can work on joint proposals. They can, as I explained, support their own work, their own research. And they can, of course, as organizations, as members, offer access to their infrastructure. And lastly, it will also be a platform where they can post announcements such as internship, job offers, upcoming events or funding opportunities and projects they would like to work on, or even concepts and ideas that they would like to research and explore further with different members within PVT Nexus. Following that, we will explore the profiles of the target audience we are aiming for within PVT Nexus. So Gintari, just change. Yes.
Yes. So my name is Gintari, and I will present actually two sides. As Mariam told, that PVT Nexus is connecting people. So we have two sides. One is mentors, and the other is students. So here we have early stage research profile. So what we expect to join. Which early stage research? So it's we are waiting for people for like master degree or PhD students or researchers within 2 years of completing their degrees, and we expect them to be like active and to be involved in PVT related researches, and also who are willing to participate in network activities and events. And also we hope to be you as like an ambassador within the institution you are studying. I'm referring now to your early stage research. That's why I'm saying you. So to promote also this network and also to tag people if you see that someone's profile fits really well here, so you can call and you can also share your insights. And what benefits you can get? So of course, within this network, you can build your network. You can connect with other peers to communicate, to collaborate. You can share knowledge. You can learn, of course. You can, since there will be mentors, you will get mentorship from them, and you can exposure them. And there will be an opportunity to explore your thesis. Of course, as Mariam told, also internship and different research opportunities. Since there will be like EU projects, you will be involved in if you want, of course, in EU projects. The mentors will be from different like research institutions and the industry side. So it's an exceptional opportunity for you to be engaged with the industry experts to get experience with maybe the different collaborative projects and so on. And through events and workshops or discussions, you can showcase also your work, what you are doing, what you are working on. And also you can get guidance about mobility and funding different schemes that there are like international mobility programs supporting research visits and project-based collaborations. Next one. And here we put, actually there is a scan. You can scan QR code directly now, the one since we launched today. So you can register if you scan this code. And here is the application form. So we ask to provide some information about yourself, to attach your CV also, and to write motivation, why you want to be a part. You have to motivate yourself. You have to motivate why you want to be accepted here in this network. And this is another site. So this is a mentors that we are welcome to join also. So what responsibilities they have? So their support and supervision, through their support and supervision, they can like foster early stage researches, to provide information, to share knowledge, to engage in different activities, project as it was mentioned before, and of course knowledge exchange. So they are like key enablers in developing this early stage researchers, this young generation, through their knowledge, through different projects, and what benefits they can have. So the mentor's name will be featured in different social media, right? They have an opportunity to share their work, their projects, their knowledge also. They can get support from students if they see that there is for instance, any topic that they need a support. They can get this from the researchers. They can foster these talents. Yes, they can equip actually through the knowledge and their experience. They can help to develop this. They can equip the new generation of researchers and all together go to reach innovative solutions. And yeah. And here is also, you can scan the QR code for the mentors. You can go directly to the website and you can register yourselves. There will be several questions to answer. There will be contact details. There will be some preferences you will have to answer, and availability and commitment. And here I wanted to show, so far until now, today we have 13 mentors sign up. Already we have in our network, so you can see that they are not only just universities. We have, as I mentioned, we have also people from industry, and also the diverse, like variety of countries we have all over Europe. So we are welcome mentors to join. Here in the room we also have potential mentors. We're welcome to join. Yes. Next one. And what we have seen, what we have planned so far. So today we are launching PVT Nexus, and until the 1st of October, we have planned that we are receiving application. We will be very active in posting, in calling for students, right? Trying to engage them to join. And then the 1st of October, it will be like first cut-off applications. It's like to have the first batch of people for the mentors and early stage researchers. And then within 4 weeks, we will have to decide, who is accepted in this network. So the 3rd of November is the date when candidates will be notified via email. And then we have foreseen like the first general meeting and launch of matchmaking platform that Mariam has already introduced. So it's around 20th of November. Just I want to emphasize that we will not like finish this year, but we are targeting like a long, just for first batch. So we are waiting for people joining all the time continuously.
Maybe I can add something to what Gintari also said here. So considering that we plan to have this as the first batch, also we envision this new network to be something, while it started within PVT for EU as a project, to outlive PVT for EU and to continue as its own network that continues hopefully for as many years as possible going forward, to be its own entity that exists beyond just a simple project or a simple organization. For example, this is something that we are aiming to complement initiative, whether within Europe or globally. For example, what Maria introduced very nicely in the beginning of today, the EA Task 73. So such initiatives are also not confined to only one project or one organizations, but they outlive such limitations. And I can say this is our goal and our aim for PVT Nexus, and that's why it is really nice to see that people are rejoining today to learn about this, and there's already a lot of interest with having very diverse list of mentors, already having a lot of early stage researchers interested and asking about this. So I hope today's launch is quite successful, and that by end of November we have a clear setup and a structure on how this network is going to go forward. I think that's about it.
Yes. And before saying thank you to audience, I would like to say thank you a lot for the team. I'm not the only one, and Mariam is not the only one who we're just presenting, but behind that we have Ivan, we have Suruch, and we have Bahare. And actually Ivan brought this idea, and then we had to roll this ball to put a lot of brainstorming, to put a lot of time, and what we have today. I think it's quite exciting today.
And it's funny how it started. It started with a rejection of an MSCA doctoral network. That's how it started. We were like, okay, we don't have that now, but I mean, it is important that we have such initiatives. So that's why we're trying to use at the moment the platform of PVT for you to at least have the initiative to start something that hopefully will become something new and something important in the PVT area, I think. So yeah, I think that I started the presentation actually thanking the team, but you were not there. It has been a lot of work. Thank you very much for the people that has joined us today. Thank you very much for the host for being here. It's really nice to see Nelson. Finally, you were first meeting a lot in Teams, and now it's good. Yeah, it's good that we met him. And yeah, I just want to encourage everyone to join the PVT Nexus and to be updated with the different information that we're going to be sharing in the different platforms that we have.